So welcome everybody to our session on 5G. We're going to spend the next 1.5 hours, or now in the meantime 1 hour, 30, 20 something minutes, talking about 5G and beyond and opportunities. And it's my pleasure to introduce, look here, I have a sneak sheet, introduce the panel. So we have Matti, who was born in, I cannot say this, Kuivaniemi, whatever, something like that. He was born in Finland. And in Finland they have these funny names, isn't that nice? So he's been working at the University of Oulu since gazillion of years, it seems like, and has been really contributing a lot in the wireless domain already, starting with CDMA, all the way to 4G and 5G and beyond, and has just been awarded a gigantomanic project on 6G research. So Matti, we're going to be sure that we're going to hear everything about 6G from Matti. Then we have Ted Rappaport, who is, these days he is, in the US at least, he's Mr. Millimeter Wave Communications. He's really pioneered have the idea of pushing for millimeter wave, not only in terms of Wi-Fi or wireless LANs, which is sort of what has been done in the 90s in Europe a lot, and WiGig is a result of that. But he's really been pushing the prospect of millimeter wave in a cellular context, and he's basically Mr. Channel sounding and channel modeling, I would say. And these days he's at NYU heading many different things. I don't want to talk about all the things you had. And before that he was at UT Austin, and before that he was at Virginia Tech. Then we have Amitava Ghosh. Amitava is Nokia fellow, yes, and he identified Rasika yesterday for us, and Ted negotiated the table for us, so we had a fantastic dinner at Rasika. Amitava has been with Motorola near Chicago for many years, and then has switched over with his team to Nokia. He's, as I said, a Nokia Bell Labs fellow. He's a very distinguished person in millimeter wave implementation, so has worked a lot with different people, also with Ted, obviously, and has been sort of the pioneer showing that 28 gigs can actually be done, and has some prospects for wireless, not only in terms of theory, but really building modems and these kind of things. Then we have David Korman. He's a program director at the National Science Foundation, the US National Science Foundation. He has a broad range of research interests spanning many technologies. Basically, he's a Mr. CPS. In his division, obviously, there's also 5G, but we have him here on the panel not as Mr. 5G, but as one of the core application areas of 5G, the tactile internet, cyber physical systems. How can we use 5G as basically a generalization of remote controls, controlling all kinds of objects. So cyber physical systems normally are just locally, but really networked over the wireless network. And so that's why it's very interesting to have him here on the panel. He has a PhD in electrical engineering from the University of Maryland, so just around the corner. And he's a local. Yes. So those are our 4 experts. And to get started, do we have a clicker, or I just use the clicker?
Yeah, the clicker's right.
Oh, there's, this is too transparent, I cannot. So I would say, let's get started with the 5G plenary and beyond, just some introductory slides from my side to make sure that, it's just 4 slides, don't worry. So we have been working in this area of 5G and trying to identify the topics of possible collaboration across the Atlantic. We assembled this expert group, as you can see here. Amitava has been meeting in many of the meetings, Matti as well. But the good news is we have David and Ted here now adding their level of expertise. So we gathered all the expertise of these people in multiple rounds of discussions and wrote some papers on that. The general strategy was to say, let's identify not the grand scale topics Why not the grand scale topics? Because the grand scale topics are so big and so important, they're going to be funded by the European Commission and by the US separately anyhow. So if it's about joint collaboration, it's especially identifying those niche topics that would be big enough to fund if you had a joint collaboration, but within each continent, it might not be big enough of a story. So that's why we said, let's talk about topics like connecting the last billion ultra-large cells. So it's actually not 1 billion, it's connecting the last 2.5 billion people or 3 billion people on planet Earth that do have GSM access but no internet. They only can get 9.6 kilobit per second. And so how do we build systems of the future so that we really can cover the last billion in many places on planet Earth? And if you talk about that in the US, it's always, oh, there's no business. And if you talk about that in Europe, it's always, oh, there's no business. But if you look at it jointly, yes, there's a lot of business opportunity. The other part is meaning 100 gigs and beyond. The third one, because there we say, currently the focus is there's a gold rush in the below 100 gigs range, but start pioneering ideas looking beyond 100 gigs is something which is probably, as we noticed in the European Commission, I had multiple proposals that I've submitted, and every one of them was told to be stupid because who's interested in beyond 100 gigs? Now we see FCC has already opened a call for ideas, so it is not that stupid. But obviously in the European Commission, it was considered to be out of reach. And so we came together and said, this is something really where we can join forces. But maybe the speed is so heated up so much in the meantime over the last months in the US that this is not a topic of joint interest anymore because the US is pounding on it already. So this is something we can talk about. A third one is narrowband IoT devices. Basically trying to understand this from a supply chain management and trying to see how we can get true global narrowband IoT coverage, also on oceans, to track containers and everything. The fourth one was ultra-wideband RFICs at millimeter wave frequencies, saying this is something that really needs to be done, and there is somehow not enough traction in the semiconductor support area in both sides. The fifth one was V2X for regional niche markets, meaning not the standard part of it, but look, for example, for agriculture. Yes, John Deere, Claas, you name them, they all need this kind of stuff to control their next range of harvesters and other niche markets like that are not so niche. Then SATCOMs, that sort of connects to the ultra-large cells again, and then spectrum farming. So those were the topics we identified as possible topics for collaboration. And as I mentioned, the line of argument is to choose topics that are not yet of the scope to be big enough to be funded in one region on its own. Now we have our panel session, and now we go in 5G and beyond. And just to get started, let's have Matti with his, and then we'll talk about some summary slides later on. Matti.
Thank you, Gerhard. Good morning, everybody. It's a pleasure to be here. Let me get going right away. We have something ongoing already with USA, between Finland and USA since, I believe, 2012. We were one of the first 2 or 3 programs that were launched in Science Across Virtual Institutes program launched by NSF, SAVI program. And we have gone through 4 solicitations, and of course the funding instrument from NSF's side has changed over the years. We have had 4 solicitations, and currently we have, I believe, 9 or 10 projects ongoing. One example is that we have joint project with TED, and there are many others. It has been really fruitful ground for collaboration. Some of our staff members collected statistics from our own group, CWC group from Oulu. Between 13 and 17, we produced 211 joint publications with US groups, coming from 45 different universities and research institutes. I would call that really extensive collaboration. I believe the numbers from other universities from Finland are almost as good as this one. So it has proven to be really, really great, and we hope that NSF will look forward to continue funding it in the future. Decisions have to be made in a few months' time if you want to go for that at the US side. I'm the national coordinator at Finland side, and that's why I'm bringing this up. Now, a couple of challenges that I would like to bring up when we talk about beyond 5G communication systems. We have to push the center frequencies towards terahertz frequency bands. This is our guess we made in 2015, what will happen in 5G. We guessed that time that 5G will be based on 4G evolution, which is pretty much the case, and we will be focusing at relatively low frequency bands. Then we predicted that there will be something revolutionary 5G, paving the way towards 6G world, aiming at serious deployment of millimeter waves, and that should take place 7 years from now, roughly. Then we also predicted there might be something on super efficient short-range radio where we really are pushing towards terahertz frequency bands, and that might take a bit more time in order to have really cost-efficient implementations in place. Of course, all this also means that inevitably, since most of the communication takes place in indoor environments, we are talking about really ultra small cells and densification in really massive scale. So this we all radio guys know that this is inevitable path, but something which is not discussed enough, I didn't want to bring it here too much for discussion, but also these changes of network architectures and radio technologies, they will definitely change also the business landscape. What are the value chains? Who are going to invest and deploy the networks? Who are offering services? We will be seeing a lot of verticals becoming stronger and stronger and deriving how our field is developing in the future. A second bigger challenge is actually this very nice white paper published by Ericsson earlier this month, where it's very, let's say, high-level discussion as it's a white paper, but they're talking about and painting the landscape. What does it mean when we want to bring artificial intelligence and machine learning to be integral part of wireless networks of the future? And some of the research challenges are coming from the real-time operation, distributed and decentralized intelligence as a part of network edge, how we go from machine learning to machine reasoning so that they really can make decisions autonomously as the different verticals will be calling for autonomous operation of wireless networks. How do we make sure that human-machine interaction is something that we humans are natively eager to jump into? The last one, but probably the most important one, security, safety, and trust. If there is even a small probability for any kind of misuse of these autonomous systems, then they are doomed to die before they are born. So many critical issues, and we do believe that this line of research should be urged these days as the development is really fast, and we have to develop profound understanding on these. Then, as Gerhard nicely also already pointed out, we very recently got really huge national research grant to focus on 6G systems for the next 8 years or so. So there was a national competition, and they chose these wireless communications and bioeconomy and related materials as the second one. There's another round of applications, and those will be launched somewhere next year. So it's 4 plus 4 year program. Volume, our budget is 251 million euros, so it's really extensive program. And we can do lots of different things. In the beginning, we have identified these 4 focus areas for our research. Wireless connectivity, devices and circuit technology, distributed computing, and services and applications. There are some buzzwords here, just giving you an idea what are the current things that we are doing in each of these areas. The most critical ones I would like to emphasize again are these device and circuit technology towards terahertz frequency bands, as well as distributed computing, making this intelligent wireless networking possible in the future. Something that was recently launched here in the US, 5G power platforms, two of those which were launched. In Europe, we have been developing similar platforms already some years. And in Finland, we have something called 5G test network, open test network, where the main parts are located in Oulu and Helsinki regions. And they are open platforms. Anybody who wants to collaborate with us can join us. Just go to follow these websites to sign in to get some more information. Our test network is commercial grade. We started to build it from the latest toys, mainly from Nokia. And we gradually augment our test network facility with proof of concept radios. For example, we were demonstrating in Pyeongchang Winter Olympic Games jointly with Nokia and Korean colleagues some 5G capabilities by using our 28 gig beamformed proof of concept 5G radio. That was shortly my presentation.
Thank you, Matti. So with this, I would say, Ted, you don't have a presentation as always because you're so vivid. But you always have statements. So let's get started.
Okay. Thank you, Gerhard. Good morning, everyone. Thank you, Matti. Matti and I have been collaborating off and on since the early 2000s when he invited me to Oulu and we drank black tar together. So it's an amazing... Pine tar. I just remember it was a very dark liquid. I had never had that. But Oulu is an amazing university, kind of in the northern part of Finland, and they have this vast research center. So congratulations on the 6G. I work at NYU. I'm the founding director of NYU Wireless, which is probably the largest research center in wireless communications in the United States. We have about 12 faculty and 100 graduate students working, and we have 16 industrial affiliate companies from most continents of the world and representing the major manufacturers of base stations, mobile phones, and chipsets for the wireless industry. We started the center in 2012, and before that I started wireless centers at UT Austin and at Virginia Tech. I thought just to level set the audience, it'd be worth taking 45 seconds to talk about what does G mean in the wireless industry. The cellular industry is about 40 years old. The Wi-Fi industry, the chips we use in our laptops and now mobile phones, is about 30 years old. Every 10 years, there's another generation of cellular. So in 40 years, we've had 4G. The first generation of cellular, 1G, was the analog mobile phone. You could intercept cell phone calls on scanners in the 80s and early 90s. And what's remarkable is 2G came along when the first digital modulation, sending digital ones and zeros instead of analog FM over the airways, evolved in the early 90s. Europe had a very interesting position in the mobile revolution because Europe was faced with the difficulty of bringing all the different countries that had different radio spectrum allocations all together in a pan-European standard so that you could talk between France and the UK and Germany all on one phone system. So they created GSM, Global System Mobile, which was the first digital 2G system in Europe, and it became very popular around the world. The US, however, took a different path, and we developed 2G in a couple of different ways. The first digital telephones were either digital cellular by companies like Bell South and AT&T back then in the early 90s, and then other companies, more maverick companies like Sprint and Verizon, took on a standard developed by Qualcomm, an American company that manufactured a revolutionary approach to cellular, which was using CDMA, or Code Division Multiple Access. So in 2G around the world in the early to mid-90s, you had two competing global standards, a US-based one, 2G, doing digital when SMS and early text started, and you had GSM evolving in Europe and around the rest of the world. So this was very interesting. In the mid to late 90s, Wi-Fi started to catch on, so now you had Wi-Fi competing for bandwidth and access to the mobile device, a very early form of that. And then 3G, this kind of US and European approach led to more advanced wideband channels where you could carry more and more data over the digital phone. And so now in 3G, your cell phone started to really become an early web browser, very primitive, but the web was starting to evolve in the early 2000s. Just to put it in perspective, 1G voice is about what your ear can hear. 2G with data is about what a small television channel would be. 3G started to become like a couple of compressed television channels. And so you had this competing European originated GSM approach evolving into the late 90s and early 2000s, and you had this US Qualcomm-based approach. And roughly had equal market share around the world. And then 4G was the first unification where Qualcomm made some acquisitions, the European manufacturers made some acquisitions, they all got together and they decided on one international standard called LTE or 4G, which all of us pretty much enjoy today in the modern world. 4G is amazing bandwidths, 5 to 20 megahertz, which means you could actually carry several television channels on an individual call if you wanted to. And in fact, it's this kind of amazing capacity that exists in today 4G that's driving companies like AT&T to acquire Time Warner for the content and DirecTV to be able to distribute wireless to your handheld device. In 5 to 10 years, it's very conceivable we'll all be watching TV on our iPads, on our small phones, on our Androids, and you really won't have much of the TV as we think about it today. Well, so 4G, there was a unification, one standard, 4G LTE, and now we're all talking about 5G, where the bandwidths now go from 20 megahertz, which can carry several TV channels, up to bandwidths of 400 megahertz or 500 megahertz, which could carry hundreds of television channels of content. Or equivalently, download a full-length movie to your phone in under a couple of seconds. So that's what 5G is, bringing this huge fiber optic connectivity to your mobile device. That's where we're going in wireless. In 2011 and 2012, my students and I did some research to show that new frequencies that had never been thought ever before to be able to work could actually provide this kind of coverage in urban areas where the radio signals don't have line of sight. Radio propagation is always a trouble. You know how your phone drops. Well, we went up to millimeter wave frequencies where you can get much wider bandwidth channels, and Monty's graphic showed that as we go up to higher Gs, you get higher bandwidth. That is the ability to carry much more capacity. So we proved to the world that millimeter wave could work, and what's interesting is the US government, the FCC, really got out in front on this. A lot of our industrial affiliates recreated the work we had done and confirmed that millimeter waves could work. And what this will do is it'll fundamentally change the device in our pocket. Our cell phone, which right now has just a few antennas, will basically become like the Very Large Array out in the southwest US with giant telescopes all beaming and looking for energy. We're going to have dozens of antennas in our cell phone, all the size of our pinky or a human freckle, all working together to grab energy, harvest energy that's bouncing off the walls, off the streets, off the lampposts, off our neighbor to create a cellular link. That's very exciting. The world's kind of uniformly agreed on this now, and there are standards activities going on, and Amitava, to your right, is actually a world expert on the standard-making process. Now, what does this all mean for Europe-US collaboration? Well, one area that's really important for the wireless industry as a whole is spectrum harmonization. So something very interesting happening right now, and maybe someone on this panel can give us an update on it, or someone in this room. The US being first in providing 5G spectrum for the wireless industry, and spectrum is the lifeblood of the cellular industry. You need radio spectrum allocations to be able to carry data. They got out in front on the 28 and 37, 39 gigahertz band for millimeter wave. These are these much wider bandwidth channels that will be part of 5G. The European community was balking at 28 gigahertz. Usually the lower frequencies, easier to design, easier to develop, low-hanging fruit in terms of making the transistors and the RF front ends that make up these wireless devices. So spectrum harmonization would be a very good thing, because when you harmonize the spectrum, you create a global market, and the chip makers and phone makers can instantly have a market that they know they can sell into around the world. This is why Wi-Fi really took off in the late 90s when there was spectrum harmonization in Europe, Asia, and the US. So that's one area I think we could work on. The other area is health effects. What's interesting is about 3 to 4 months ago, there was a study that came out by an Italian group which said today's cellular down at low frequencies, 1 and 2 gigahertz, are maybe dangerous. US had a similar study, came out about 2 weeks later, that said there's no evidence for carcinogenic effects of cell phones. We did a lot of research on this 5 years ago when we were starting our wireless research. We wrote a paper that the National Institutes of Health has made open public called Millimeter Safe for Generations to Come, where we studied the effects of millimeter wave, and it turns out the human body is very reflective, so very little energy is actually absorbed. And any carcinogenic effects we postulated based on all the research we've looked at hundreds of studies in Europe, and a lot was done in Russia, to see that it's really heating. It's the effect of RF heating that could lead to health effects. And as long as you don't have RF heating, generally these low frequencies, 5 orders of magnitude below the ionizing radiation level, beyond the band gap energy where there's an ion that's split off, these are very safe. So it'd be interesting to find out. Right now there's a disparity in the safety factors. Europe's about a factor of 10 more conservative on how much RF energy is allowed to be than the US. So that would be a good thing that we could unify together. But early evidence shows that all of these cellular frequencies, even going up to millimeter waves, are still so low in frequency, 5 orders of magnitude lower than the frequencies at X-rays and gamma rays that are known to be carcinogenic. And we've studied this. I'm in radiology at NYU, and it's known that the carcinogenic effect of ionizing radiation, X-rays and gamma rays, is caused because these radiating waves have enough energy that they can split the electron out of the valence shell of an atom. And that atom now becomes unstable, and that's what leads to other growth. But if we're 5 orders of magnitude below that, there's not enough energy to, like the cue ball in billiards, to knock out that electron to cause this kind of carcinogenic issue. So my belief is millimeter waves are safe. I believe today's cellular phone is safe unless you get RF heating. And so that's another interesting area of study we could look at. Finally, I think one of the key issues that the industry faces, and it'll be interesting to hear Amitava's view and also NSF's view. What I see in engineering is there's so much interest in what we heard about yesterday, big data, machine learning, artificial intelligence, that we're seeing less and less interest of young students wanting to get into the engineering in the United States of creating telecommunications, new protocols, new theories, new coding theories, the technology that goes into cell phones. See very aggressive energy and investment in Asia in the telecommunications space. But I don't see it in the US. Students are kind of going away from the area of communications and going to computing and big data. So the question is, where are we going to get the future generations of students that can do the ingenuity and create the technology and the standards that go into 6G and 7G and so on. I'll stop there.
Thanks, Ted. So with this, I just have to make one little remark because it's very typical that a US guy stands up and says the market share of CDMA and GSM was the same, because in 2010, that was when both sort of peaked. There were 500 million CDMA phones and 5 billion GSM phones. So that's how numbers become same. I guess you're starting to tweet soon. With this, let's have Amitava have the floor and give his points.
I disagree with you kindly, Gerhard, on that comment.
It's just the US part of the market share, not the world.
So thank you, Gerhard. Thank you, Ted. Thank you, Marty, for your presentations. And I'll give an industry perspective of what is going on in the industry. And the whole goal of 5G is to make our lives better. And what we see in 5G is the interaction of man and machine. So the man and machines are integrated to make our life better. Eventually, in 100 years, the machine will take over and the Skynet will be operational in 100 years. That's what I predict. Okay, so the first phase of 3GPP is done. It is release 15. The specs are out. The commercial version of 5G will be deployed sometime next year, middle of next year, end of next year. And it covers all frequencies. What I said, usage of both sub-6 gigahertz and millimeter wave spectrum. We have this feature called massive MIMO, both at sub-6 gigahertz and millimeter wave. We have this lean carrier design, flexible frame structure, scalable OFDM-based interface, scalable numerology. We have advanced channel coding with introduction of LDPC code and polar codes for control channel. Then LTE is not going away. We have the aggregation of LTE and 5G carriers. And for millimeter wave deployment, one of the key things is integrated access and backhaul. Without that, it is not economically viable to deploy a millimeter wave network. We have flexible connectivity, beamformed control and access channel, whereas in LTE, the control channels were not beamformed. In 5G, everything is beamformed, and the higher spectral usage. The spectrum situation is, say, 600 megahertz in North America. We'll be deploying LTE and 5G. Actually, T-Mobile US will be deploying 5G at 600 megahertz. We have 3.4 to 3.6 LTE 5G deployment, and then we have the 28 and 39 gigahertz, which are for hotspots coverage in Korea, Japan, and US. Moving forward, you see, in 5G, we'll have the combination of low and high bands. 5G is not millimeter wave, it is a combination of sub-6 gigahertz and millimeter wave bands. So you see the low bands, so the low bands are used for IoT and critical communication, mainly for massive MTC. You see, and I don't think you need 5G for that. You can get by with LTC, LTE-M, or narrowband IoT. Then you have this mid-band where we are deploying 5G at 3.5, LTE at AWS band, and you can get 10x capacity with LTE grid and massive MIMO. And then you go to the hotspot situation where you get 1000x local capacity as you go to millimeter wave bands. So we are using high bands for capacity, low band for massive MTC, and low latency critical communication. Now, what is coming in? What is in release 16? You see, these are the study items which have started. So these are the non-orthogonal multiple access. From my perspective, I don't see, you will get 10, 20% improvement. This, I think, is very important, non-terrestrial networks, which includes HAPS, high-altitude platforms, satellite communications, etc. Then this V2X, this is important, integrated access and backhaul and unlicensed spectrum for 5G radio. So these are the study items which have already started. And these are a slew of proposals which are being considered. So this air-to-ground communication, location enhancements, which is key to 5G, 5G above 52.6 gigahertz. The millimeter wave which we have, which have been standardized, is for frequencies below 52.6 gigahertz. I don't know why this particular 52.6 was chosen, but anyway. So these are some of the expected proposal, and guess what? These are the RAN 1 items. So in the recent meeting, which concluded last week, these were the things which are approved. So it means this is the RAN 1 led items, which is further enhancements to new radio MIMO, new radio V2X, new radio unlicensed band, NOMA study items, and non-terrestrial study items, then UE power consumption, NR positioning, etc. So these are the things which have been approved as study items and work items. So suggested topics for EU-US collaboration, I think it aligns with what Gerhard and Ted had. I will say NR-based V2X at millimeter wave. That is important because V2X has already been standardized probably for LTE, but you need terabytes of data, and to do that, you need millimeter wave. So this is one area of collaboration. I think this is a great promise, air-to-ground communication. I think in disaster scenarios and public safety scenarios over the seas, this balloon-based communication is very important, and we need 5G for that. Then machine learning, that's a buzzword. Everybody is working on machine learning. So I think I have looked into this. Let us see what can physical layer deep learning, how can we implement deep learning in physical layer? Can this be achieved? And these are all the basics which needs to make Skynet achievable, you see, or viable. Then this is one important thing I like to emphasize, that how you deploy millimeter wave. what is the strategy of deploying millimeter wave? Because there are a lot of issues. You have this 200 millimeters coverage in a mobile environment, and you have this issue of blocking and penetration. So how do you handle millimeter wave deployment? Can you use deep learning to do this? And of course, 5G above 52.6 gigahertz terahertz communication. This is an area which needs to be investigated, and part of this is the RFIC development. But I think from collaboration point of view, US is very sensitive to export control with respect to RFIC technology, so that needs to be sorted out. So these are my suggestions, and I have, Yanning told me to give a presentation on terahertz communication, and I have couple of slides on that if you want.
Yes.
Do you want me to present that?
Yeah.
Okay. So I want, how do do that?
Later in the breakout session.
Yeah, in the breakout session, we'll present that. So this is all I have. So this is very promising. I'm really excited, and I agree with Ted. Everybody wants to go to investment banking. They don't want to build bridges. They want to build dreams, you see, all the students. That's my issue, you see. They want to go to investment banking. They want to go to big data. But the nuts and bolts of engineering on how to build bridges and dams, they're not doing it. And that is where US is falling behind on that. And the brightest is going to make money. Okay.
Thanks,
Thank you.
Amitabha. So after having this deep dive on the technology, now, David, you're going to give us some ideas of how CPS is going to help 5G make money. Yes?
We'll actually see what we're going to have. So, I'm interesting when I got my doctorate at Maryland. It was in controls and networking. I went into the controls side and really haven't done much in networking for many, many years. So, what I'm program director. I lead two fairly substantial programs at NSF, and both of those have direct applicability to kind of the landscape of advanced wireless and providing kind of the glue that enables. So the programs I lead are Smart Connected Community Program, which is around a $20 million annual budget, and the Cyber Physical System Program. Cyber Physical System Program over the last 4 years has spent roughly $40 million a year. Now, all those really pale in terms of the 251 million euro. I was really impressed by that kind of number. We can only aspire. Okay, so, wrong way. So, some motivation. Why do we start talking about advanced wireless networking and some of these capabilities? In part, it's really what kind of networking foundations do we really need if we start to think about smart connected communities and the applications that really will help make people's lives easier. An important part is we don't call this the Smart Cities program. What we really look at is connected communities. Connection is the networking part, and the community part really means it doesn't simply have to work in a city. It could work in a small town. It could work in a rural region. So we're looking at something that's broader in scope than just cities. Interesting point that was raised earlier about where people are really working these days. One of the things that we have really thought about are what are the technology needs of communities? And here are just listed a few of those. You mentioned the big data analytics, sensing, control, automation, things like cyber physical system, health and wellness. One of the newer things that we have going is human technology frontier, where the question really is, will AI put everyone out of work? It's a tough question. And socio-technical questions. Those are kind of technologies and needs, and what those result in are a set of investments in programs. So those investments in programs include things like cyber physical systems, smart and connected health that uses networking infrastructure, big data with hubs and spokes, robotics, National Robotics Initiative, importantly, the fairly large security program. In fact, the SATSI program, Secure and Trustworthy Cyberspace, is probably the largest multidisciplinary program at NSF. And one of the key ones that I'm going to talk about is platforms for advanced wireless. And part of that story, though, is that kind of creates a model that NSF has started applying over the last several years in terms of creating platforms, creating public-private partnerships, and using those as a vehicle for advanced technology, for funding advanced research. So wireless networking at NSF, let me go back to build it, there are many different research programs within the wireless area, investments on the order of $75 million a year, and it's fundamental to much of the work that we see published today. One of the good parts and one of the things that we look at in terms of an overall NSF portfolio is the vibrancy of a program. And so when we look at things like CPS, NRI, advanced wireless, our NET's core programs, one of the ways that you look at is, are there a lot of startups that are being generated? Is there technology transfer to industry, in addition to how many papers get published? All of those are key elements that we look at. And let me let this build. And what we are looking at in terms of advanced wireless is taking a lot of theoretical ideas in terms of networking capabilities and seeing, can we really get those to work in practice? So ideas on massive MIMO, spectrum sharing, and full duplex upload, download capability. All of those kinds of capabilities are really critical to enabling the applications that we see today, either in a smart connected environment, in a cyber physical system, in operations with drones, and really almost any of our infrastructure systems. So that leads to Platform for Advanced Wireless Research, which is the start of kind of a model that NSF's developed. So one of the issues is, and I've been a big backer in the ideas of test beds. And so I worked a number of years at Boeing, involved in a number of DARPA programs that were really test bed programs. One of those was called Software-Enabled Control, where Tariq Samad was one of the major performers. I worked on the platform side, and the idea was you need a platform to enable high-fidelity research. And that platform should be scalable, both something that academic researchers can download, utilize in their laboratory, should include a hardware-in-the-loop element, which enables you to start to take research into the real world, and then a test bed that enables you to actually not just test things in a laboratory, but bring things into the real world. In my background, it was really, let's fly things over the desert. Let's actually see, do these work? What happens with reflections? What happens when systems bank and antennas lose coverage and you have signal dropouts? So the idea is you need things that go beyond toy data sets. You know, in many of the research that we see through NSF, you start with toy data sets, but you really have to advance into real world. We want things that are repeatable. We want things that we can publish, and we want to be able to learn from our mistakes. What that leads to is, one, the idea of public-private partnerships, because when you start to look at test beds and the kinds of things you might want to actually build for a wireless, wireless platform for research. They're not insignificant funding. And one of the issues is always, it's a very competitive environment. So how do you get people to both provide funding to enable research, have the government provide funding, and the only way to do that is, one, start to look at what are the enabling pre-competitive research ideas. And we start with that through the National Science Foundation. We want open access test beds. People can plug in their capabilities in the real world, and we want to bring in industry funds. So we started this this idea goes back several years at NSF, where we started some programs with Intel. So NSF, Intel, CPS security was one. There's some ongoing programs further with Intel and VMware. It's a model that we like, and it enables us to grow our portfolio without having to take money from other programs. So what are part of the platform for advanced wireless? I have to give a lot of credit for these charts to Thiaga Nandagopal, who proves, one of the things that this chart proves is that, one, NSF can work with industry, and two, NSF program directors actually talk to each other. I think there's some suspicion that, you talk to one program director, you can tell him something, you can tell another story to someone else. We actually talk to each other and enjoy each other's company and share projects and ideas. So there are a number of charter members, including both hardware and software vendors, software developers, a number of them that were mentioned today by the panel. In fact, I really learned a lot more about 5G and beyond than I knew before today. And what this provides is really drivers for success, which are reproducibility of results, actually building in an operational context. It's critical, interoperability, so essentially getting rid of technology silos and open access. Open access to researchers as well as fairness in access. So it doesn't mean that everyone has to have millions and millions of dollars of platform availability. They can use this. And it enables discussions on usability, programmability, diversity. So NSF is part of the platform for advanced wireless. We're doing 4 city-scale platforms, 5 years of funding, and $20 to $25 million of cash and in-kind, plus NSF funding. So there's a power project office. Glenn Rickert is part of it. It includes, the project office helps to work the selection of specific projects, working to build the platforms, includes US Ignite and Northeastern, and enables working both across industry and with the research community. And the important part is early stage research that really enables the development, creation of these new wireless devices and the technologies that people at this conference are really talking about. And what is one goal? It's revolutionize the wireless ecosystem, maintain US leadership in the sector. So what is that really? Let me just briefly, 2 of these are the Powder platform with Salt Lake City, looking at massive MIMO base station, ending programmability, diverse spectrum access, and Cosmos cloud-enhanced open software-defined mobile testbed in New York City. There are other activities going on in New York City from the smart and connected community perspective. One of those is a small edge computing project with University of Arizona, I think Columbia, as well as the Harlem Silicon something. which is really an exciting project in terms of providing bandwidth for others. It's an application-driven environment for experimentation. So the idea is what applications does it enable and what can I do well with it? And back to your point, how do I get people to work? Most of these rely on things like computing, machine learning. The actual engineering side, so the bridge building, in fact, if you look at the kind of ideas we get, those are all machine learning for sensing and active control type things. So many of those engineering principles are really being replaced by the computing and machine learning. And there is some need to look at what does that next generation do. So let me throw out a couple of ideas. One is, what does collaboration really mean? And I think it was brought up yesterday, a couple of models. One is the researcher-driven, essentially, I have collaborators both in EU or other countries, a US researcher, and it's really an informal ad hoc collaboration. One of the challenges that we see at NSF, and I can talk to this from our smart connected community perspective, we actually were soliciting, in our webinar, we said, you know, it would be nice if someone had one city, one community in the US, one community outside the US, and brought in research both from the US side as well as research sponsored by a outside, could be an EU community, could be somewhere else. And we really didn't get much response from that. And one of the challenges I see is that at the individual research level, there's a tendency to think, you know, we'll do workshops and all this, but in terms of building a big project together, it requires almost a bilateral type of arrangement, which is kind of the arrangement that we have with Finland. We've had arrangements like that with JST, Japan Science and Technology. We're discussing ideas like that with other countries. But unless the researchers talk together and start bringing funding sources together, that collaboration may be very informal, very ad hoc, may be very productive, but it doesn't necessarily produce a larger scale project. And those larger scale projects are things that, to some degree, when we look at the kind of technology needs that integrate the control, communication, computing, and essentially building cyber-physical systems together, those bigger applications don't necessarily come together. And that's kind of one of the areas that we're certainly interested in from the NSF side and might be an interesting source of discussion here. Thank you.
So thanks, David. So if we look at different topics here, let's first have a little round, and then we open for questions from the audience. Obviously, we touched all kinds of different areas. We touched technical areas, of which obviously sort of the, let's say, Matti, Ted, and Amitabha were talking about 100 gigs and beyond, yes, going to the next generation of frequencies. Then we also had basically David touching on power, or however you pronounce it, or sort of.
That's it.
And saying that we possibly have to make sure that we don't only do theory, but we have to test the stuff to make sure that we really influence the industry. And I'm certainly a big fan of testbeds. Now, let's start out with that, David, if I may. Yes, and Ted, you can jump in because you're part of one of the power guys. So as a person that has built possibly the biggest academic testbed so far, with 27 cells in downtown Dresden, covering all of Dresden, to show basically that coordinated and multi-point distributed MIMO can be done, and convincing everybody, every company on planet Earth and cell that came to visit us and go into the testbed, I saw the impact. But that was a testbed with an intent. We did all the theory. We couldn't convince anybody because they said, if you don't test it, it's not going to be convincing. So we built a testbed for an intent. In the case of power, there's no intent. So that for me is the question, how can you convince a PhD student to write a thesis on a testbed where I'm not going to prove something to be good or bad? You know what I'm talking about?
Interesting.
So a testbed, just to be a testbed, that's like if you look at the testbed, I mean, the 5G IC in Surrey is doing the same. They're building a testbed to build a testbed. Yes, and if you look at the traction of the 5G IC's testbed, it's almost zero. I don't know, Matti, if you see it differently, but I mean, so the question now for me is, if we're talking about just to get the testbed thing, and then we would like to possibly move on to 6G topics, but I want to understand that a little better, because this could be sort of a generic kind of understanding mismatch between motivating a PhD student to show the planet Earth that my idea is right, or just to build up a toy.
So part of the idea of test beds, so you're right, you don't build a test bed to build a test bed. You build a test bed in order to prove, in order to, one, create a stimulating environment that enables you to develop the component technologies, the research that plugs into the test bed, which provides kind of the rest of the services and environment that enables you to prove that, hey, my component technology can actually work in a larger scale environment. And that type of research is the kind of thing that shows, one, you can write great papers, you can get published, you can get further research funding to do it. So it goes from the idea into something that I can not just do a laboratory scale
Exactly.
test, and I can actually test it with other services and learn from those, the operating environment that it's placed within, to see, one, collect a set of metrics on the performance of how does my idea perform by itself.
That's why I would have seen like the 5 different test beds or 4 to really have sort of an intent, each and one of them, to prove to planet Earth that some idea is going to be.
Let me add to that, because it's a fair
maybe
question.
it's not being shown. That's
No,
what I'm
it's
saying.
a fair question, because generally in engineering, computer science, we build things purpose-driven. And your argument is, why put all this money into something with no real purpose other than to be there to provide a platform? There's a number of value points that need to be explicitly said that maybe you haven't recognized. One is, there's huge value in the integration and creation of a pseudo commercial grade network, a testbed that can actually accommodate many different visions and many different applications. There's huge educational value. The vendors providing the equipment in kind learn a lot, so there's some educational value. The second thing is, it's kind of like venture capital funding. You're providing this thing, you're making an investment, you don't know what's going to come out, but there may be 1 or 2 good ideas out of every 10 or 20 that actually lead to a new technology breakthrough, that lead to a new concept. There are some test beds on the West Coast that actually led to a couple of startup companies that got acquired for very high values and actually created part of the technology that's used in 4G. So NSF has some wins in these test beds, even though we don't know exactly what they are. In the case of the New York City test bed with NYU, Columbia, and Rutgers, we're taking an earlier version of 4G WiMAX and rolling it out to 50,000 households in Harlem. So there will actually be low-income users of the technology that we're going to try on the test bed there could be new applications, new services provided, not just for the human value, but also the fact that you can't put your ideas as an academic or even industry onto a commercial grade network. You can't go to a Verizon or a T-Mobile and say, I've got this new idea for compression. Let me try it. They're not going to let you put it on the network.
Amitabha, maybe you want to add something? Yes?
Yes, with the PAWR, what I see, they are too late because 5G will be commercially deployed next year. So what value PAWR will add? If they had deployed this 4 or 5 years back, it would have been of great value, but they are too late on this.
Okay. Now, if we look at Amitabha, if you look at what Matti is doing, yes? He's getting 251 million euros funding, I guess, at Oulu alone? No. Just Oulu. Just the university. Yeah. To address 4 topics, of which only one is new, right? You said ultra-reliable, low-latency communication, that's 5G. Mobile edge cloud, that's 5G. Applications, that's 5G. But terahertz electronics, that's new. So how on earth can you pull that kind of a thing off?
First of all, the targets for this national flagship were twofold. You have to keep doing international standards academic research, plus you have to make great impact to society and industry. This impact for society and industry we do through our 5G test network. We are helping industry to demonstrate and pilot lots of 5G evolution versions as well through our testbed.
Okay, so you're actually buying equipment.
Nothing to do with the equipment. We already have it.
But I mean, 251 million, that's over 5 years or whatever it is. It's, I don't know how many people, but at least, I don't know what kind of salaries you pay, but like thousands of people.
Not thousands. Let's not go into the budget details. but yeah, it's big one, and actually it will cover, our faculty is currently of 500 researchers. It will cover all of our faculty plus some more. But anyways, I would like to go a little bit back to this 5G test network thing. And I agree with Gerhard that you have to be really focus driven and you must have a purpose for doing that. Our purpose from day one was that we want to demonstrate new capabilities for future operator business models. We have been talking about micro operator based business model which relies on local spectrum licensing models. And our government is going to make in a few months' time decisions, and we hope that the answer is positive, and yes, we can launch first national 5G micro-operator company as an outcome of our 5G test.
Gerhard, I want to make one point that follows on what Matti said, to challenge your argument and challenge your position that power is too late or this is too much money. Don't underestimate the impact of what these kinds of grants do for things behind the scene that grease the wheels for future telecom. In the New York City example, you may argue that the power award from NSF is too late to have an impact. But what that grant did is it allowed us to go to the mayor's office in New York City and actually free up fiber optic access that the city owns to provide for this test bed. And in doing that, it challenged the city to think about making more availability of its fiber for commercial services, for carriers that you sell your equipment to. And similarly, Matti, as you do this, you're going to illuminate carrier weak points and kind of bring out pressure points from unexpected places. This is the value of fundamental research. So even though the testbed made too late on a technical
I don't know if it's fundamental research if you're using WiMAX, which sort of lost out.
Well, that was years ago. That was a previous testbed. This will be 5G.
Okay.
But the point is, it creates things behind the scenes that gets partners to think a new way, and it opens up markets.
But Ted, one of the things I like to point out, the 5G, which will be deployed, the first version, it will have all the components of edge computing, network slicing. It will have gigabits of data rate.
But here's the problem.
frequency.
The industry is developing this 5G. You saw the slides. You presented them on a timeline that is so furiously fast, you don't have time to think about and look at more advantages and more capacity. That's the land of academia, where we can try things and bring out new technologies that eventually will filter down to industry.
So that's the question. So I want to see, for example, a virtual reality application where I sit in my home and get the experience of a stadium. Can PAWR do that? And that's the thing, use the components of 5G technology and give me something which
Here's
is
what power does.
far-fetched.
Here's what power does. It allows some professor or some small startup somewhere to have that idea, to have that application,
Okay.
to come to New York and put it on the network and prove it. I can't go to a Verizon and do that.
But Matti, you still wanted to complete. Or are you done with your...
No, not quite, not quite. So how do we spend this huge budget? So we really do see that our field is going through a major change. Although there are big challenges related to this high-frequency radio engineering, there's no doubt of that. But even with current level of radio connectivity capabilities, we have hell of a lot things to do at the network side, how to make it truly autonomous, efficient, intelligent, how to provide all these future verticals needs, even with 4G technologies. That we are very far away from that. So we have to involve a lot of new disciplines. We have to understand enough of different verticals like health or autonomous car industry or energy sector, you name it. So we have to really spread out, and that's going to need a lot of resources as well.
So one of the topics you discussed, and Ted mentioned it, and Amitabha mentioned it, and David mentioned it, was machine learning, deep learning, whatever. So obviously it's a buzzword, and it was one of your quadrants and one of your slides. So is it a tool like algebra or calculus? Fantastic tools, don't get me wrong. I love that math. Yes, but for us as engineers, it's a tool that we also research on advancing the tool itself, or do you see this as an application in that? Because that's where I didn't quite get that part of it. Because Amitabha was talking about as a tool for improving the PHY. That's how I understand you, right? And you were talking about it as sort of like almost an application, getting whatever real-time deep learning is.
I think it's a little bit of all of those and maybe even much more. But if you think about dynamic distributed computing, it's a huge challenge, even theoretically. And as we know, mobile cellular systems are extremely dynamic and extremely difficult to model even. And when we break it down to lots of small cells, it's going to be even more messy. And we have different types of spectrum and spectrum sharing and spectrum usage. It's a huge mess. And how can we really automate different things? For example, at physical layer, how can we learn from what happens on the street? For example, when we do pencil beam forming, maybe we can learn from where are the users typically going to do initial beam acquisition, etc. So there's a lot of really useful applications, but we don't understand that well enough, in my opinion, yet.
Yeah. So with the neural network, so you have the input and the output, and what you need to do is to train it, right? So you use 5 days of training, and it is all based on history. And
Well, there are two types of training, right? There's the one online training and offline training. Those are the two different major approaches.
yes. So it is. So you do the training, and then can we do a more efficient algorithm? For example, right, MU-MIMO, how to pair the users, right? Can you use the history to pair the users efficiently? So that is for channel state information. So with this beam forming, you receive channel state information from multiple transmission points. Can you use machine learning to simplify the process? For millimeter wave deployment, so you look at each pixel and to see whether this UE is blocked by certain events, and then predict that what kind of modulation we'll use, which base stations it will be connected to, so that we drop the outage rate. So I am talking about concrete ideas on machine learning, and machine learning is always based on training, and the training set should be very elaborate, or you have to. It should be very intensive, so that we get proper results or efficiency out of it.
So can I?
Yes, David?
Okay, so one of the questions you asked, though,
Yes.
is when we talk about, so part of this is collaboration.
Yes.
And so one of the questions, and power is an idea for collaboration within certainly a U.S. ecosystem.
Right.
So the question really is, how do you push real collaboration, U.S. and EU? So, for example, what our friend from Nokia is talking is really, okay, these are great Nokia investments, development of new standards, yet that's not necessarily U.S.-EU collaboration. It's Nokia-U.S., Nokia-EU collaboration. To some degree, the question here, I think on the table is really, how do we, what defines U.S.-EU collaboration in this space? What are the opportunities that go beyond perhaps, I know in the CPS discussion yesterday, yes, we create workshops that we bring U.S., German, Japanese, other researchers together, go to Hawaii, go to Germany, go to Japan. That only goes so far.
Well, the good news is Thyaga on our stage at the Brooklyn 5G Summit this past April said that these power test beds are open to anyone, Europe, Asia, anyone.
So
can
David, your
participate.
question is basically, what is the format? Because, I mean, the workshops are happening. We don't need
Right.
NSF.
Yeah, no,
IEEE is doing
that's exactly my point, which is
Exchange of information. We are doing now exchange of information. That's all. But
right.
what are the
That's
concrete steps?
right. That's my point. Is the power is an open test bed, so it's kind of you come, and we can work with you, but that still isn't. That creates an environment that can foster collaboration, but it doesn't itself generate. It doesn't build essentially, okay, I'm a researcher here in the EU. I do want to play with power, but I need to get funding from on the EU side. Perhaps I have a US partner working together. So the question really is, how do you grow this collaboration, then go beyond these very informal things?
So what I'm, see, we are doing all these Picasso workshops, and which is good. We are exchanging information. The thing is that we don't have a set for the EU-US collaborations. We don't have a set of deliverables for dates with dates and what exactly we are doing. That's what is lacking, you see, and that's what needs to be flushed out.
And that was my point with, so NSF has done a few of these, and our friend from Finland has brought some of those up. And so kind of the question really is, what is the right model? Or what are the right models that can really go beyond the informal and actually build these put larger ideas together and essentially grow things in a more organized way?
Here's an idea, because I've seen this work in America very powerfully with the NSF engineering research centers. The ERCs, especially the first generation of ERCs, really brought a set of committed faculty who, from all different disciplines, and worked very, very hard together to create a culture of interdisciplinary research. Maybe there needs to be a joint EU-US ERC vision. Very large centers, I mean, big money. Maybe not up to your level, but, maybe an order of magnitude less, but, several tens of millions of dollars that get several faculty from the EU and US really committed on a vision. The ERCs have a target. They have a kind of a pseudo-deliverable, a vision to change the world, to make impactful change. I was lucky. I was a grad student in one of those at Purdue, the first one in intelligent manufacturing. That's where Wi-Fi came out. I wanted to do wireless in factories, and there was no wireless communication. That's just one example. There were many students that did a lot of different things. So maybe that's what's needed, a big, focused ERC-type cross-continental program.
Or maybe not so big, because maybe the distance means that you just want 3 here and 3 there. So, but that's a different story.
Well, you
I don't
need a
know- I don't know
culture.
if
I
bigger
think
is
you're getting
better.
to the cultural issue and a focus and a drive and kind of a moonshot with a lot of people working on the same area.
Because sometimes what I'm saying is big centers, just having geographically local makes them more effective than scattering all the money all over the place. Like you have like these billion-euro flagships which are all over.
I think the first generation ERCs in the US were more effective because they were generally at one institution. I think as you saw later generation ERCs spread around the different universities, I don't have any concrete data, this is just anecdotal, but maybe they didn't make the impact that the first or second generation ERCs.
I think a strong signal or message should be sent to Commission in Europe. They have a tendency to spread out the money all possible countries on the planet. Small amounts, very small amounts.
Breadcrumbs.
So it's not even enough for travel funds. Just the last example, this Brazil thing that we are both involved with. So, and Gerhard and myself, we have been involved with many international programs through EU. And I have to admit that working with US groups is very natural. We have the same cultural background. We don't need to learn to understand each other's thinking, and that message should be sent out. When we work with Brazilians, Asian countries, it's very difficult. I would not like to say impossible, but close to that sometimes. And if they see the value and the, let's say the similarities of the needs of industry in US and EU, they might actually be willing to pour some more money.
Okay, questions from the audience? Yes, in the back.
Thank you. Stripping, this question is for Dr. Rappaport. Stripping, and my name is David Bain. I'm with the technology, I'm a wireless entrepreneur, as well as a member of the nonprofit Technology Safety Council, which is concerned with digital wellness and well-being. So stripping the electron, or not stripping the electron, may not represent a comprehensive and holistic test of whether a device usage is safe. My question for you is, would it be an area for broader collaboration to look at the broader principles for safe device usage, safe for self, safe for society? Perhaps, just another idea to throw out there, if the ship has sailed on 5G standards, that could be a direction that power or Nokia money in Oulu could be directed towards. Find the guy who makes the pine tar juice or something like that. Maybe one or two of those 500 people could.
Ted, do you want to take that?
Yeah, I to your fundamental question, is there room for broader research on safety of wireless devices? I think absolutely. I think it's appropriate and needed. It's always good to have more information, although it's hard to prove a negative. And I was offering the valence electron issue as a way to fundamentally explain why it's known and acknowledged that X-rays and ionizing radiations above the gamma rays and X-ray frequencies are known to be carcinogens. They are known to be because it can be proven and there's a physical effect. And my point is we're operating at so many orders of magnitudes at lower energy levels that that's not a viable way to induce the known carcinogenic effect. So I think it's worthwhile studying other things. And by the way, safety is not just radiating energy. It's also the use of the device, texting while driving. There are so many issues that are transforming the way our society works. If you walked in downtown Manhattan or DC and almost walk into people that are on their, looking at their smartphone, I mean, that's a safety issue. The fortunate thing is 5G and 6G are actually going to address this. The wireless device will soon have a radar that will image and have virtual augmented reality, so you can look at your device and it'll tell you if you're going to walk into someone in the next few years. That's coming. People are working on that. There's patents filed.
And people are working on having basically red lights in the pavement for
Yes.
pedestrians. So that
So there's a lot of activity, but these devices are changing the way humanity lives, and there's a need for safety study in those areas.
second question from the back, Eva, and then Svetlana.
Yeah, thank you. I was listening to the question from David, where are we going with the EU-US collaboration in 5G? And I found it very interesting that this question came from him, because there has been a call in the Horizon 2020 program and in the NSF program on collaboration. Well, these two calls have been pointing to each other, so there should have been some collaboration through those two calls. But I also heard that there was some kind of mismatch in the expectations from each of those. And I was wondering, where are we going in EU-US collaboration in 5G? Is there any perspective?
6G, let's say 6G. 5G is done. David, you want to take that?
So could there be some kind of collaborative program that gets developed? Sure, there could be. One of the critical points is, and I go back to a couple of years ago, we had a CPS EU summit, and the real question that gets asked at both sides is, what's the value proposition in terms of how does the US side benefit from leveraging, say, EU or other international research, and how do the other countries, the other participants, what value do they get? And we've demonstrated that value in the kind of bilateral activities that we've done. So could there be one in 6G? Yeah, there could be. Again, one has to start diving into the real details of what that collaboration would mean in specific areas of benefit to each.
Freezing Svetlana. You look cold.
Thank you. You mentioned, so my question is about mechanism of collaboration. You mentioned that perhaps engineering research center is a model, but you have in the US university industry cooperative center funded by NSF, about 50 of them, right? And we have, they have international members, okay? And as far as I understand, research results are pulled together for the benefit of the companies. And we have in Europe also, we have clusters with industrial participation with university. What do you think about this way of collaboration?
But the funding mechanics is very different. In Europe, the company gets money to carry out the research. In the US, the company provides money to carry out the. So in the US, it costs money. In Europe, I get money. That's a very different funding mechanism.
But you are speaking about European programs, okay? But I'm speaking about for clusters. Yeah. They have industrial funding. For co-funding, okay? So it's also co-funding from industries. I'm not speaking about European research program. I'm speaking about.
Yeah, there are a number of IUCRC programs in the U.S. I was the director of one of those. I'll be quite candid. The money level was pretty low, and there were intellectual property right issues that made it difficult to be an entrepreneurial university. And so it was easier for me to go directly to the companies where I had relationships and had trust and ask them to fund. And the companies trust us with no IPR agreements to do good research and to help them and to get them students that can graduate and go into their companies. So unless the funding level is significantly large enough, it's hard to attract, I think, the kind of focus and talent and real game-changing energy to create something. And that's why I go to the ERC model. That's why I think Matti is well-deserved. If you've ever seen his university and what's happened in Oulu, it's just amazing, the potential and the capability and the talent that exists there. It's as well as the pine tar. But it's fascinating. So unless you have a critical mass and really fund it, it's hard to get the buy-in of faculty. I mean, look, the problem with academia is all these faculty are, companies of one. It's hard to get collaboration to happen unless everyone is really bought in and wants to change the world, and you get their attention by putting money, and that's why the ERC is at a kind of a level. I think a cross-continent cross-Atlantic ERC model could be very effective. It's a very small investment to get the buy-in of a lot of good minds to really work on one thing. It could happen because we have a model.
The very last question, and then we're asking.
Do you think this 5G technology will result in lower cost data plans per month, or do you think it will actually cost more to have a mobile device in your pocket?
Great question. I think everyone should answer that on the panel. I'll give my first answer. I think if you look at what's happened in the semiconductor and telecom world, it's unbelievable the value we get per dollar we pay. The money we pay now for bandwidth access is probably what we paid 10 years ago, and we get so many orders of magnitude more. I think the value to us as a consumer will continue to go up per dollar. That's my belief.
Yes, I think the prices will come down eventually, yes. Because you see, for millimeter wave, the base stations will be all in one, small form factor, and the technology should be there so that you can deploy it really it is automatically using self-organizing network and stuff like that. So it'll get cheaper, you see, where the price point will come down both for devices and infrastructure.
David, do you want to say something?
Actually, my point, it would be great to see the device price go down, because what we've really seen lately is the device, with the Apple 10, the device prices essentially reaching almost a stratospheric level. And the interesting question is to relate this to models in third world, in developing countries, where the wireless access has to be much cheaper, and the wireless devices are similarly many times less expensive.
You see the carrier subsidizing that device price, though, a lot.
Matti?
5G will change how the networks look like. Like Amitabha said, that they're coming into household, small form size equipment. But it will not happen if spectrum regulation is not going to support it. And if it supports it, the whole value chain is going to be changed. We are not only under the mercy of mobile network operators. You can become your own operator. You can lease some of the capabilities of the network from bigger operator, and so on and so on. So I don't think we are not addressing enough yet the change potential that 5G will bring, and that should be even discussed amongst us researchers.
Yeah, to Marty's point, there will be private industrial network, right? So where a private like you and me can operate this network. So this is one of the key things, 5G, private industrial network.
So for me, I always say 5G is like the first Carl Benz automobile. Yes, you take a carriage and put a motor underneath, and that you call a car. And 5G is exactly that. So 5G, we're testing out so many new things like network slicing, low latency, ultra reliable, low latency, tactile internet, you name it, you got it. It is a bag, a millimeter wave. You're testing out everything on planet Earth at once. So 5G for me is just a big testing standard, debugging standard for us to learn a lot and then make 6G happen. Now, talking about your cost, obviously we will also have to learn about pricing, because I do believe the ARPU, the average revenue per user, should go up, but not necessarily per device, because we're going to have not only 10 devices, but hundreds of devices connected to the network. And obviously, so to make this a viable business, the ARPU has to go up. And we'll see how that happens. That's my point on this. So with this, let's go into the coffee break and enjoy an earlier start of the next session. So have fun. And thank you to, of course, to our panelists. And for those that want to go spend time with us in the breakout session this afternoon, you're more than happily invited to do that, where we're probably going to be talking a lot about terahertz communication.
And IoT.
And IoT.
All right, I think we're ready to begin. This is our last plenary session on the future of autonomous systems. I'm David Shaw, and I'm the Vice President for Research and Economic Development at Mississippi State University, and I am a co-chair of this panel, along with Hayden Thompson, who we'll introduce in just a moment. Very much appreciate the opportunity to be actually in this position. Yesterday and today, I feel like in many ways have built toward this, in one sense, kind of being the culmination. We've talked about big data, we've talked about cybersecurity, talked about advanced communications, and talked about privacy policy. And here we're going to be talking on a number of those aspects with the applications of autonomous systems. You simply cannot pick up a newspaper or go online any day and not see some conversation going on about the tremendous opportunity and the tremendous challenges that we face with autonomous transportation, both aerial and ground-based systems. Safety and privacy are particular concerns that are expressed, but the untold opportunities and just simply the imagination that's going into the applications of these technologies really lead to a tremendous amount of excitement. We have a wonderful panel that's a mixture of the European and American interests, academia and industry, and so I'm very much looking forward to the conversation that we'll be able to have. This morning I've asked each one to give a little bit of their own background from their perspective as it leads to the position that they represent today. Our first speaker this morning will be Al Severus from the Center of Autonomous and Cyber-Physical Systems at Cranfield University in the United Kingdom. Our second speaker is Dallas Brooks, who is the director of our Raspet Flight Research Laboratory at Mississippi State University. Hayden Thompson, who is the CEO of the Think Group in the EU, is our third speaker. And then finally, Malcolm Glenn, who is the Director of Strategic Partnerships with Uber Technologies here in the United States. I've asked each to speak for about 15 minutes so that we make sure that we have plenty of time for questions, both from the audience and conversation amongst ourselves. So with that, Al?
Thank you. So good afternoon, everyone. As Dave said, I'm Al Severus. I'm from Cranfield University in the UK. We are just about half an hour north of London. We are a postgraduate university research, so most of the work we do is really on research projects, the majority of the work. We have a couple of campuses. We have the Defense College and the civilian side as well at Cranfield. What I'm going to be talking to you today about is just to give a very short presentation, about 10-15 minutes, to just describe some of the issues and challenging about aerial platforms, specifically the unmanned ones. It's very difficult to try to cram too much in a very short presentation, so but it just gives you a flavor of the things that we are looking at and the things, some of the challenges going into the future. So looking at the history, just a timeline to give you an idea as to where we are with regards to unmanned systems. So if we look at the manned aircraft starting from the beginning of the 1914 and so on, and if we put a parallel axis to that one with regards to unmanned systems, you can see, to give you an idea regarding the comparison, as how fast those platforms have been developing and moving forward into the future from this point of view. So what you can see here, and it's specifically, it's one of the greatest growing areas here in unmanned system, and I put that chart here specifically from Tractica, and basically this is not about the growth that you'll see in all the other graphs that you see, but an actual revenue that is expected over the 2015 to 2025 period, and you can see this one here in terms of how many billions we expect. And the majority of growth is really, as you expect, in the US, Europe, and the Far East, and basically China, Japan, and these kind of areas where where there's a lot of interest, especially for maritime surveillance, for environmental surveillance, and those sort of applications. And if we are to try to break down, to give you an idea of where the majority of, or some of the application where these people were expecting it to go forward from here is, as you can see here, the breakdown, and a lot of it really actually to do with Earth observations, and the other bit is really to do with the border and security and surveillance. Especially this is, there's many projects being going on in Europe within Horizon program and security, and the European Defense Agency, which is looking at monitoring and surveying the Mediterranean for illegal refugees. And as I mentioned to you, and following on from these conversations we've been having for the last couple of days, what you can see, it's really the main enabler of this technology has been the enormous growth really in sensors. So if we are to look, we are to correlate how sensors have been developing over the last 50 years, and we do a line here to compare to the autonomous systems, you can see that the majority of the development has happened in the last 20, 30 years, and is mainly driven by the sensors, because the sensors open new areas of applications. And with new areas of applications means that we are able to use those platforms to carry out more missions and more complex missions. And this is now is driving being exponential. Of course, we don't let this at some point will flatten out, but we're moving to different type of sensors, different kind of applications, but maybe we can have that in the conversation. The other slide I wanted to show to you here is with regards when we look at the unit cost versus the number of units that are being produced. And again, looking at the two major drivers have been the automotive industry and the mobile. And what is interesting about this is how you can see how the magnitude of the cost drops as the number of units gets into hundreds of millions and so on. But what is interesting here, and the point I want to mention here, is that we still have only just started to get into the IoT. So IoT, up to this point, or to 2016, hasn't really been a major contribution into the drone or unmanned systems area, autonomous systems. But this is something that what we expect will drive the next, if you like, revolution in terms of the use of autonomous systems. But of course, as you all know and you heard on the news, etc., unfortunately, the word drones have a bad reputation, but there is quite a lot of challenges. And what I'm going to do is, these are the typical challenges we used to have 20, 30 years ago, trying to get those platforms up in the air. However, these are now, most of them have been addressed, or we are quite advanced in terms of understanding how these platforms behave, and we can get quite easily them up in the air for various missions. However, what the big challenge now is for us is how we can integrate those into our airspace. So, of course, if we talk about small platforms, remotely piloted platforms, then we are down here at the low risk. But when we're talking about an autonomous passenger aircraft or a cargo aircraft, then we're talking about full UAS integration to the airspace. And just to give you an idea, there is a lot of interest at the moment, especially driven by a group in the Netherlands, in Europe, where they're looking at how we can use other corridors that are not used currently for passenger jets, like for example over the Arctic, in order to have a cargo airplane operating in that kind of airspace. But what is clear from here is that we cannot just move straightly into complete autonomous platform, but it will be a step moving towards that. So, and a lot of this is really because of the regulation. So the reason why at the moment things haven't been moving so fast as we get with, for example, with the autonomous cars is our perception, if you like, or society's expectation about safety. So if we look now back in 1945, we look at how the public demand for safety assurance, and you compare that to, if we look here in today or 2018, you can see for the different platforms what the public demand for safety compared to what it used to be in 1945 for the different platforms. And of course, when it comes into people getting into aircraft, etc., we are right here at the limit of, zero risk, because we all try to get to where we want safely. So what are some of the key challenges we're facing at the moment? Of course, certification and standards. So this is the typical areas at the moment where there's a lot of work and some collaboration between the US, of course, and Europe going on into this area. But the other challenges of thought is regarding with the decision-making system. Because if a platform going to be certified or standard being established in the US or in Europe, and this platform has to travel from one place to the other, then we need to make sure that, these platforms are compatible and the systems are, we're able to have some traceability. And then as we move forward, a lot of these technologies as well are also applicable because of the cost to manned aviation. I'll just briefly have a slide on this one, and this is basically the reason why I put this one. This is one of the biggest programs I'm aware of that had 3 stages, which finished the third stage finished about 4 years ago. It's called Astrea, and this is looking at civilian side of getting unmanned air system and technologies into non-segregated airspace. And to give you an idea about this program, it is just around 90 million. Equivalent of 90 million US dollars or close to 100 million US dollars. We've involved all the major companies in the UK, academia, and research institutes. So, as I explained to you before in the previous slide, what we were looking for is not the technology about, your guidance, your autopilot, and all that sort of thing, your flight control system. But there's our new challenges that are coming nowadays into the new type of aerial systems. And I want to emphasize those 2 areas you see there on the left-hand side, which is really the unmanned traffic management, and that is a big hot topic area. At Cranfield, we're building a new center called DARTEC, Digital Aviation Research Center, and we're investing 100 million, equivalent to 100 million US dollars, in building that center together with 5 industrial partners and a 50-50 contribution between the research council and the industrial partners, for example, Thales, Raytheon, and so on. And one of the things we're looking for here is how can we get, I'll show you a little video of some of the ideas that I got from, we get it there from about concepts of how those systems will work in the current airspace. And the other thing which is very of interest is, a lot of people, as you see, the sexy words nowadays about AI, and well, how can we certify AI systems which are not deterministics? And finally, regarding connectivity, this is again linked to our DARTEC, and what we're looking for, and we got some projects working already on this one, is looking on cognitive radios, software-defined radios, 5Gs, and Aeromax. And our main interest really here is quality of service, depending on the traffic. So we need to start thinking slightly different about how do we see in the future UTM compared to what we have at the moment with ATM. So at the moment, you have your air traffic management, which all centralized. But if we're going to be looking into the future in UTM, then we need to start thinking about maybe a different way of how we do that. And what I mean by that, a decentralized approach. So that's a short video from One Sky, just to give you an idea about the concept of what how do we see UTM being integrated in the airspace. So you have all your NOTAMs, no-go areas, etc., and so on. And then this is a typical approach, for example, in a small SME or an end user wants to get from point A to point B, and then he can sit there and plan that on a little interface. So you can see there's the no-go zones, and wherever there's no time, then he can put the waypoints as to where he would like to go, etc., and so on. And the altitudes, of course, whether it's a fixed altitude or different, taking the terrain into account. And then you have the UAV flying out there to do the mission, flying from point A to point B. Another issue which is really been skewing the development of unmanned systems, and I'll just finish that with my last couple of slides, really, it's the security. There's a lot of concern at the moment when it comes to security, especially with regards to the security agencies and how we can control or monitor all these unmanned platforms that are flying out there, and really not the big ones, but we're looking at those little small quadcopter ones that are flying out there, and that is a big issue. What is interesting there to see is that nowadays you have a whole industry, and this is expected to grow by 2024 to $2 billion US, which is looking at how we have, if you like, an anti-drone industry of how we can bring those things down, whether it's using lasers, which seems to be one of the most promising approaches at the moment, and some other electronic countermeasure, etc., and so on. But you can see how things at the moment are changing in this landscape of us not developing the platforms, but maybe controlling them or bring them down. So some of the issues here we have. So in the past, we're talking about some of the policy changes. So we're talking about here some of the vehicles in the old days. We used to be how we can get those a single pilot flying a single platform and that sort of thing. Today, we're talking a little bit about swarms and having a pilot flying maybe multiple vehicles, talking about the certification aspects, and operating beyond line of sight in order to open this commercial avenues for these platforms. And what is interesting is where we're going into the future. Okay, so talking about, maybe a new certification process where AI is part of it, for example, about the data, who owns the data. Would you allow people to fly over your houses? Would this platform need to fly over the roads? That sort of thing. Privacy, of course, the communication. We heard about 5G earlier and so on. And I cannot say much about it, but there will be an announcement, a very exciting announcement in this area at the Farnborough Air Show. So keep an eye on this for next month about personal air transport. And with that, I'd like to finish my presentation and thank you for listening.
Pardon? So his question was, who will make the announcement?
I cannot say now.
You have
It's
to
a
be
UK.
there.
It will be done by the UK.
Thank you. Our next speaker is Dallas Brooks.
Hello, everyone. I'm Dallas Brooks from the Raspet Flight Research Laboratory at Mississippi State University. We do a lot of unmanned aircraft systems work at Raspet. Walked in this job about 2 years ago, and it's been full speed ever since, so it's been fairly enjoyable. Whoa. Apparently I'm freaking out the machine. There we go. That's me. I've got a little bit of a varied background, 26 years in the Air Force, the last 7 of which was at the Pentagon. I had a series of jobs where basically I was the first to do just about everything that in unmanned aircraft systems the whole time I was there. So I was the first Air Force Chief of UAS Integration. I was the first chair of the Office of Secretary of Defense UAS Task Force. I was the first DoD FAA liaison on unmanned aircraft systems. And so I was sort of writing my own job description as I went, which meant I got to leave a lot of the boring parts out and just do the parts that I found interesting, which was a lot of fun. You don't normally get opportunities like that at the Pentagon very often, where you get to be somewhat creative and sort of define your own path. But it was a very fulfilling 7 years for me. And were it not for the birth of our son, we probably would still be here. But one of my challenges is I have a speech impediment. I can't say the word no, so when people keep asking me to do things, I keep doing them, right? So I ended up with a lot of different jobs. So in addition to my day job, which is as the director of RASPIT, I'm also the sitting chairman of the board for AUVSI, which is the largest trade association in the world for unmanned systems. I'm also the associate director for the FAA's UAS Center of Excellence, which is a consortium of 24 universities, both national and international, that the FAA uses to do directed research on key UAS integration topics. And then I co-chair, you can see this alphabet soup here, it's a very long string, but I co-chair an outfit called the UAS Science and Research Panel. And that was born, actually I co-founded this in DoD back in 2011. And back then, it was just to get the 4 services on the same page about how we were doing UAS integration, detect and avoid, things like that, because everyone was off doing their own thing. And so I was fortunate enough to be able to take all their money and then say, you're not going to get it back until we start working together a little bit better. It was an effective approach. It worked. We began laying out structures, all the major muscle movements for detect and avoid, our systems development strategies, all those things to where they, even though the purposes were slightly different for the services, we got the opportunity to say, here's our framework. So work within this framework. We'll have a certain amount of compatibility across systems, but more importantly, we'll have a lexicon. When we say that this is this, we'll know that that's what it means. And that was a big challenge early on in detect and avoid. With any success, things start to grow. So once we started being fairly successful in defining some key terms, such as what does it mean to be well clear between an unmanned system and a manned system? In other words, how much do you have to miss by? Other agencies started saying, hey, wait a second, can we get in on this? And so it went from DoD to DoD and FAA, and then DHS, and then NASA, and then most recently we've added Interior, Justice, Commerce, and Energy. So, the last 4 don't have a lot of money in their UAS programs, but they do want to participate in the research and help set the priorities. I can tell you Interior is doing a lot with small UAS, particularly in firefighting, wildfires. And Commerce, mainly NOAA, are their major UAS customers. Energy does a lot, obviously, for some of the things that they do everywhere from they're using unmanned systems for nuclear verification, for example. Let's see, formerly, UAS Integration Chair for the OSD, I talked about that a little bit. Military Director for the Policy Board in Federal Aviation, that was a fun job. So the Policy Board is a consortium of the air chiefs of all 4 services. So the DCS Air for the Marine Corps, the A3O for the Air Force, whoever runs the air for each of the services is the representative to the policy board. And so those general officers get together and they decide, here's what we need to be able to do, here's how we need to be able to fly, and then the policy board works out with the FAA how they're going to do that. So if you have a unique military requirement, for example, that you need to be able to fly really high and break a couple rules while you're doing that, and you need to be able to coordinate that with the FAA, that coordination is done through the policy board. And we also do a lot of waivers for military aircraft that are just not going to get updated with new types of technology, for example. My lab, we have 2 55,000 square foot hangars. One is dedicated to advanced composites materials research and development, and the other is dedicated to unmanned aircraft systems. I'll talk about the UAS here because that's what we're here to talk about. So federal UAS research, that comprises about 80% of RASPIT's funded research. It's on the federal side. Our customers, you see a lot of them up there. The FAA is a big one, DHS a big one. We work with NOAA, we work with the Office of Naval Research, U.S. Geological Survey, the Naval Oceanography and Meteorology Command, and then ASSURE, which is the consortium of universities that I talked to you about. That's the FAA UAS Center of Excellence. I'll start with the DHS piece. This was sort of a national competition to win this. DHS had been doing some very limited UAS sort of tests and evaluation. They had taken this on a sort of a science project. What they found were that a lot of local law enforcement agencies, disaster relief agencies were going out and they were buying unmanned aircraft systems with no true understanding of whether or not they could fly them or how they could fly them or when they could fly them, and without a good grasp of which systems were best suited for mission needs. And so DHS Science and Technology Division took a look at that and said, we can help with this. So they staked out some land at Fort Sill, Oklahoma, and they started to basically invite UAS vendors in to demonstrate their capabilities within the context of DHS mission sets. So it might be a Secret Service mission set. You know, it might be Homeland Security, Border Protection. It might be First Responders Group. It might be any of those things. So in a disaster relief scenario, they might have a flood scenario, simulated flood scenario, and say, show me how your system is going to perform in doing the assessment of the conditions, the triage of the damage, things of that nature in a flood scenario. And do that again for a wildfire scenario, and do that again for a Secret Service shooter scenario. And as they refine these use cases, and vendors came in and had a very targeted way of saying, this is what we think we can do for you, they sort of built a database, sort of a consumer reports book, actually, on if you've got this mission, this is probably your best combination of sensor and unmanned systems. For this mission, here's your best combination, and here's why. So the reports ended up being fairly detailed and very helpful to the law enforcement and first responder communities. But DHS wanted to blow this up. So rather than doing little exercises in Fort Sill, Oklahoma, they wanted to do full-on major exercises with UAS running over the top. So it became not about the UAS anymore. It became about a full-scale border protection exercise and with UAS incorporated. And so they wanted to do that with flood, with fire, with chemical spill, with rail disaster, with highway disaster, with presidential movement. They wanted to do everything that the agency did, full speed, fully staffed, anywhere from 40 to 4,000 actors, and with UAS over the top. And that was a major, major endeavor. So the state of Mississippi bid on this. We put together a statewide team. You can see some of the mission sets that were there. DHS was serious when they said we wanted to do a rail disaster. Part of what you had to write to was, we were going to take a real train and we're going to push it over. And then we're going to run our scenario, and then we're going to clean it up when we're done. They wanted underground train scenarios as well. They wanted, again, you had to be able to flood an area with buildings in it. I mean, this was major infrastructure stuff. So our partnership was built, headquartered out of Mississippi State University, but primarily focused on the southern part of Mississippi because we have some fantastic assets there. Camp Shelby Joint Forces Training Center has been around 100 years. They do everything. You can blow things up there. You can shoot things. You can set things on fire. You can run UAS over the top of all that because they have restricted airspace. I see you smile. Let me tell you, it's fun blowing stuff up. It really is. I don't care who you are. When you blow something up, it's a lot of fun. Singing River Island is the former Pascagoula Naval Air Station, and so it is literally an island just off the coast. Long bridge that goes to it. That base was closed about 10 years ago, and it well preserved. They didn't let it go to seed, and so I've got this fantastic facility where I can go launch off the southern coast of an island and have the entire Gulf of Mexico as my playground. And I'll talk about the airspace situation there in just a second. And then our friends at Stennis Space Center, because NASA is NASA, and they bring a lot of good things to the table. So I talked about airspace. One of the things we've built over the last 2 years at RASPID is one of the most robust airspace capabilities in the world for UAS operations. Everybody says they have airspace. No matter who you talk, oh yeah, we got tons of airspace. Problem is they can't access it, at least not with an unmanned aircraft. So your airspace has to be very specifically characterized for unmanned systems. In the US, that means a COA, which is an FAA instrument that is essentially a waiver to fly unmanned aircraft systems. Or you can be in restricted airspace, which is government owned and is prohibited from other aircraft from entering into it. So if you have permission to be inside of it, you can do essentially whatever you want, and that's a lot of fun as well. And then we have things called warning areas, which is sort of restricted airspace that's offshore over the water, and they start about 13 miles out off the coast. So between COA airspace, which is FAA designated for UAS use, restricted and warning areas. We're running, about 8,000 square miles, anywhere from the surface to 60,000 feet, depending on where we are. We spend a lot of time laying that groundwork, tremendous amount of coordination. We have letters of agreement with the applicable FAA centers, with all the military agencies, so we can fly what we need to fly almost anywhere we need to fly, and that includes beyond visual line of sight, which we can do in both the restricting and the warning areas. So big aircraft going very long distances with corridors in between some of our COAs, so we can leave a COA. You see the corridor there between Starkville and Ackerman, the little box in the line. We're looking at increasing our corridors to where they span the entire state. So we've been very fortunate to have a great working relationship with the FAA and have the ability to fly almost anywhere we want to fly. Again, we focus on larger aircraft. The one I'm showing you here is the Outlaw G2. It's about, it says 150-pound gross takeoff. Ours are beefed up, so they're really about 180. 30-pound payload for our models and 15-foot wingspan. So all of my stats are actually wrong because we bought the souped-up version. 6-hour endurance and a 50-mile range, and that range is not. That's as far as it can fly. That range is as far as you can get from the antenna. Day-night operation. We're adding to our capability this fall, picking up 2 new Navmar Tiger Sharks. These are about 500-pound aircraft, carry about 100-pound payload for about 12 hours. Ground control station, 28-foot. Everything that's built into there, we built into ourselves. 2 simultaneous operations at any given time can be conducted from this station. We roll out the trailer, generators, everything self-contained. So whenever we get somewhere, it takes us about 45 minutes to set up, and we're ready to fly. I had a great video that went along with this, and I didn't copy it on. It's a shame, but 2 minutes long. This is Dauphin Island, Alabama, which is a fantastic place to fly unmanned systems. 3,000-foot runway, as you can tell, sticks out into the water. As soon as you get off the departure end and hang a left, you're in the Gulf. And since we have permission to fly from literally one end of the Gulf to the other from the FAA, we were able to do a tremendous amount of research with the twin-engine Griffin Sea Hunter aircraft. So we did bathymetry with LiDAR, mapped a good deal of the Mississippi Gulf Coast for the Office of Naval Research. The FAA UAS Center of Excellence, this is probably one of the most important initiatives that the FAA has come up with, and certainly the most productive for UAS integration. So the FAA's track record on UAS integration is a bit spotty and tends to take a lot of time. It's glacial, actually, in progress in some ways. But this is where they got it right. So the FAA has centers of excellence for a lot of things. There's one on general aviation airports. There's one on commercial space transportation. There's one on advanced materials for aviation manufacture. And at one point, the decision was made that we need a center of excellence for unmanned aircraft systems. All the centers of excellence follow a similar model. They're a consortium of universities, usually leading in their field in whatever their particular area of interest is. They band together, form a team. They're centrally run with one lead, and the FAA gens up, here's our research requirements, hands them over to the Center of Excellence, who parcels them out to the appropriate universities based on their core capabilities, the ones that are best suited for that kind of work. The universities bring match to the table in this arrangement, so if the FAA is kicking in $400,000 for a project, then the university is expected to match that with $400,000 in value. And that can be actual dollars, that can be faculty time, that can be industry contributions, both time and money. But it provides fantastic value for the government. And it allowed the FAA to immediately put key researchers on a lot of these fundamental problems that we have when we try to integrate unmanned aircraft systems. Here's our membership list. Like I said, it's 24 total, and I think there's 4 or 5 international. Concordia, the Technion, Southampton. There was one other I think that did not make the slide. But Mississippi State University is the lead agency for the Assure FAA UAS Center of Excellence. To date, you can look at the list of some of the research projects that we've either led or participated in from the Mississippi State perspective. The top one is a brand new one, just awarded. So they have asked us to anticipate the Amazon vision. So e-commerce networks, our transportation engineers are going to build the model for aerial drone delivery networks across the country. It's going to include tie-ins with logistics centers, ground and air, airports, trucking. Literally we'll model where those drones will be working from, the distribution centers, their ideal routes to get them to the areas of highest traffic, which would be in a lot of areas that's your more upscale suburbs of folks that are paying for that kind of delivery. We're going to do the safety analysis to say here are the challenges that we see. Here's the risk factors. We'll have to quantify those. The model that we build is intended to be flexible and reusable to where we can literally change 5, 6, 7 variables and see what that does to the safety equation. So it's going to be an interesting project for us. Take us about 2.5 years to get the whole thing built, but it's going to be fun. Two of the most important things that we've done, ground collision and airborne collision severity. No one ever knew how bad it is when a UAS hits something. So we had all sorts of data on what happens when, for example, the Range Commanders Council, what happens when a piece of shrapnel hits you, what happens when a softball hits you, what happens when another blunt object hits you. But what happens when a UAS hits you? Is it the same thing? And there just weren't any data. So the Assure Coalition got together and we literally started, first we built the computer modeling piece of it, and then we started firing UAS and components of UAS out of a cannon at various things, right? And then we dropped UAS onto the heads of crash test dummies. And then we dropped UAS onto the heads of human cadavers. Kid you not, I didn't do that research myself, thankfully. Because it turns out that you have to have a fresh, unfrozen cadaver if you're going to measure the shock wave that goes to the brain in a concussive event. And concussive is one of the issues for UAS trauma. Laceration is another, blunt force trauma. So the true measure of what could happen to you when a UAS strikes a human body, depending on where it strikes you, how fast it's going, how it's built, what it's made of, is it frangible, is it not frangible, where the engine is, huge thing. And then we did the same set of tests against when a UAS happens to hit an aircraft, right? So hits a windshield, goes through a jet engine, right? Hits the leading edge of a wing, what happens? Again, materials become extraordinarily important. One of the things we found was that a rear engine UAS does less than 1/3 of the damage of a front engine because that center of mass in the front with a sharp propeller shaft will just drill right into anything. It'll absolutely destroy it. Whereas a rear engine UAS, whatever's on the nose, it's usually the payload, when it strikes, the mass is towards the back. So it's gonna start to move up, start to move out. It's gonna deflect. And so that simple design consideration of front or rear literally triples your damage in an impact situation. And so this kind of research is already affecting how people build UAS because they know that if they build the same UAS front engine, their chances of getting it certified in certain situations are not what it might otherwise be. We're a FAA UAS test site through a partnership with Pan Pacific. This allows us to be able to bid on certain projects for the FAA and for NASA. We already had tremendous capability walking in the door, so we were invited to join their team as part of a coalition, for lack of a better term, to build a super site. And that's it.
Hayden Thompson will be our next speaker, and shifting gears and going towards the ground vehicles.
Well, actually, you shouldn't need to shift the gears. Should be autonomous. Right. Okay, so I'm going to talk about autonomous ground vehicles. My background. Oh, sorry. I'll go down. I'm quite short. So my background is quite unusual as well because I started my career in flight control systems. I've worked for the US Army firing lasers at stuff. You don't get big explosions. You just drill a hole through things. I've also worked on the Joint Strike Fighter, on the lift system for that. I've designed flight control systems for Boeing. I've done all sorts of stuff. And I run a research centre for Rolls-Royce for 20 years and ran something like 400 projects during that time on lots of different technologies, including some on Astrea as well. So I've been involved in many of these programs and also on military programs like SWAV, which is another program in the UK. So today I'm going to say something. The worn out. Oh, right, okay. That's why I can't say it. So quickly something about Think then. So Think is a company which is based in Europe, in the UK and in the Netherlands. We also have a branch in Japan, and we also have our autonomous systems division out in Australia. Why Australia? Because there's a lot of open space, and there's not too many regulations for overflying and things like that. And the key thing we're interested in is smart anything everywhere and anytime as well. So we're really interested in providing monitoring or trying to get data from A to B in some way. And we work in lots of different areas. We work in Formula One. We work in Formula One. We work in the nuclear monitoring area, self-powered systems. We work with NASA on some stuff in remote monitoring. We have these microgenerators. There's a video of this, but I won't show you. Basically, as you shake it, it generates power. We're interested in sort of self-powered devices for the future. We also are interested in UAVs in the oceans, but also UAVs for flying around. And we're also interested in Internet of Things and getting data from A to B. So we actually have an interest in big data, IoT, 5G, all of these different technologies. So if I go on there, and we're also doing some interesting stuff, even looking for sharks off the Australian coast as well, using UAVs. And it would be quite interesting to see whether you could fly a UAV into the shark and see if it caused some damage to it as well. that might be quite useful.
It's almost as fun as blowing stuff up.
Yeah. So we're interested in lots of weird and wonderful applications. Now, I'm coming today to talk about automotive area. I also work in the automotive sector quite a lot. I work for the European Commission quite often. Most of my time I spend in Brussels covering things like AI, the automotive sector. So I sort of cover autonomous cars for the European Commission and also for the European Parliament as an advisor. And also other areas like 5G, big data, and those areas. I also have some oversight in that area as well. So the thing we see in autonomous cars is basically that we're seeing things which are quite common across a number of areas. We're getting autonomy in cars, in the train area, also in aircraft, as we've seen, and also in ships as well. And so we're finding that increasingly we're designing the human out of the loop in the control of these systems. Now that requires the technologies to do that, and we need to be able to do that. And here we get into areas like AI and all these other technologies. We're also interested in optimizing traffic flow. So congestion is a big problem. So you sort of saw some of the maps there for aircraft where they're flying around. There's all the restricted zones and things. If you look at the number of drones, which are around by 2015, about 1 million, I believe, by 2015. So there's lots of these things flying around, and it's a big issue. We find with autonomous cars, we need to try and deal with the optimization of the traffic flow. We have the same sort of problems in the rail sector. Also, the aircraft sector, we're looking at 4D traffic management and also traffic management for the oceans as well, particularly in areas where it's very, very congested. And the other key area is actually health monitoring. So we also want to monitor systems as well. So these systems are very complicated, but what we want to do is try and increase capacity. We want to get greater safety for systems. So what the key thing that's driving the use of autonomous technologies is to try and improve the safety of the overall systems. And we also have a benefit from the environmental benefits as well, for reducing emissions. Now, the big challenge really is that if you look at the global car fleet, it's predicted to be double, actually to about 1.6 billion vehicles by 2030. And we know that's not sustainable, not with the existing infrastructure we have. So without integration of information and flow control systems, we're going to have severe congestion. All of our cities will be clogged up. Our motorways will be clogged up. So we need to do something. And indeed, this is seen as a big market. Already by 2020, they're predicted it's nearly $18 billion, this market, and it's expected to grow. So it's good news. All of these challenges are always opportunities. Okay, so the first thing which is interesting is the communications in this area. And so it must be said in Europe, they've been working on communications, car-to-infrastructure and car-to-car communications, and a standard for this for about 10 or 15 years already. And there are various different standards being talked about. So you have WAVE in the US, we have ITS G5 in Europe, and various other things floating around. But the critical issue is really that the car market is a global market. If you're selling cars, you're not just selling in Europe or America, you're also selling in Japan, China, etc. So you need to think about the worldwide market for these. So you need a global standard that everyone can agree on. And The other thing which has been noted really is that if you're talking about putting wireless communications into infrastructure, really the lead in this will be from countries where they have significant private infrastructure where they will invest in this. So you're looking at countries like Italy, you're looking at countries like France, this is within Europe, Norway, etc., where they can invest in the technology. Okay, now the thing which I must say that is driving the communications connections to cars is really the infotainment industry at the moment. It's not so much the autonomous car industry, it's the infotainment industry. And this is where we hear about 5G, we talk about transferring, getting TV to your phone, etc. Now there's two types of connection. We find that we have these embedded connections in cars, but actually most people these days just put their smartphone in the car and have a tethered connection. And that has all sorts of advantages. So a few years ago you would have had a TomTom with your maps on it. Now you use the Google Maps, I'm sure. Now that's interesting because TomTom, if you use a product like TomTom, you then get into product liability. So if they get it wrong and you drive off the road somewhere or go to the wrong place, it's their problem and you can sue them. With Google, you can't do a thing because they're just providing an app. So it's a bit of an unfair playing field for some of these technologies. Similarly, we find with music apps is that it's replaced the radio which you would have in the car, and so we're getting these connections. So there's lots of advantages for this. Also for the automotive companies, they can do recall on different applications. There's a lot of software in a car these days, about 90 million lines of software, typically in a modern car. And they also can analyse the performance of cars as they're running. And a lot of car companies are doing this now to actually understand how their cars are operating out in service. And also they're looking for ways to actually cross-sell products for the future. So the infotainment market is big. So the connected car market is big. And we're sort of seeing they're talking about, okay, about 82% of cars will be connected by 2021, which is a lot of cars. It's going to go by a factor of 10 from 2015. So we're talking about a lot of cars going to be connected in the future with a big market potential for that. If you look at the lead companies in this, it's companies like BMW, Daimler, etc., and General Motors. Now, the question mark is who's going to make the money out of this? So we're providing this connectivity, but it's actually other companies like Microsoft, Apple, Pandora, Google, etc., who are likely to actually make the money out of this change. Now, when we get to autonomous cars, there's different levels of autonomy. Now, you may well have seen this before, but basically, currently we're at the level of we've got automatic braking systems, we've got lane keeping control in cars. As we move to the next level, we've got to level basically where we still have a steering wheel, so we can take over control if something goes wrong. If we go to the final level of this, which is level 4, we get rid of the steering wheel altogether, and there's nothing you can do. You're just sat there as a passenger, and you just hope that the system works. Now, that's okay, because we're designing these cars for people who may be disabled or might have limited mobility in the future, but it may be that they might be drunk or something like that, so you probably don't want them taking over the control of the car. Now, in terms of the technology, there's different levels of technology, and most of the car companies, it must be said, have developed a lot of the technology to enable this to happen. So all the sensor technology is pretty much in place for this. And if you look at the predicted opportunities, if you break it down into the different tiers like LiDAR, radar, optical cameras, etc., all of that technology is there, but the challenge is to try and reduce the cost of that technology at the moment, because we're very much down to the last cent in the automotive industry. The key thing to note, though, is this black band here. That's the software, and that is the really big opportunity for the future. It's in all of the control software for these systems, and so that's where people are positioning themselves. It's a huge market, and we can see that, okay, we're talking about billions here, and we sort of see that there's lots of different things we're talking about in terms of the different levels where we might actually provide that. Okay, there are some barriers as well. So there's lots of advantages. We talk about saving lives, we talk about fuel savings, we talk about traffic congestion, we talk about economic stimulus to countries. But there's also challenges. The challenges are things like consumer acceptance, so trust of these systems. Would you step out in front of an autonomous car? Would you sit in it and let it drive you somewhere? There's some interesting videos on the web of people who've sort of sat in these cars and get totally freaked out by the concept. The high cost of the technologies. So there's two things here. First of all, the cost of making a fully autonomous car is still quite high. The Google car, for instance, is about $150,000 of strap-on kit you need to put onto the car. But also there's things like, okay, we can put in these fancy processing boards into cars, but they consume a lot of power at the minute. So we've achieved a lot with convolution neural networks and image processing and things like that. But if you're talking about electric cars, it will be a major drain on the battery. So we need to have much lower consumption. And typically they're talking about 400 gigabits per second of data being transferred around the car. So there's an awful lot of data which needs to move around. The big concern, though, is, okay, when we roll these cars out into the everyday traffic, because we're going to have a mixture of cars. If everything was autonomous, it would be great. It would make life easy. But because we're mixing with manned drivers whom we don't really know how they're going to react, then that is a challenge. And we're going to have accidents. There's no doubt we're going to have accidents. And so the question is, how do we deal with that? Because every accident will be high profile in the press, as we've already seen. But you've got to weigh that up against the ethical question of the fact that if you reduce the overall deaths on the road by a factor, and you're talking about saving hundreds of lives and hundreds of accidents every day, if you weigh that up against a few accidents that might happen in the future, you need to think about that. So there's a need for intensive real-time monitoring as well, because if something suddenly stops, if a car suddenly stops in the middle of the road, you need to know about it. And so we then get back into the issues of privacy. And so we have to take more information about the cars, about who's actually in the car, where they're going, etc. And it could also be used for law enforcement, for how fast they're driving, if they're breaking speed limits, etc. So do people trust these systems? So it's quite interesting, because there was a survey performed in the US of 1,500 drivers and also executives of companies. And the interesting thing was that actually 55%, so over half of them, said they would actually buy a fully autonomous car within 5 years, which is a surprise. And the remainder of them, almost all of the remainder of them, said they would do so in a 10-year time frame. So people are more accepting of the technology than you might think. Now, the big problem is, okay, how much are you going to pay for that? And so at the moment, about 20% would pay $5,000 for this, for some of the features. So there's a need to think about, okay, the pricing of this. So the benefits are increased safety, lower insurance and fuel costs, which are all benefits. And we can see that potentially the first applications of this will be in highway and traffic jam autopilot modes, but then moving on to urban autopilot in the future. And it must be said that Japan and Western Europe are predicted to be the first adopters of this technology. There's lots of stuff going on in Japan. They're doing a whole load of mapping of all of the road networks in Japan, so they can drive even if there's snow on the roads at the minute, so that they can actually drive cars autonomously. So there's a lot of things going on. So we see lots of different market predictions. So if you look at all the different there's market predictions, but there's lots of different ones. What they all say is basically we won't have fully autonomous cars until about 2035. So it's still some way off. We're going to have highly autonomous cars, or a lot of highly autonomous cars on the road, but not fully autonomous. So already we have ADAS systems, advanced driver assist systems, and partial autonomy and full autonomy is moving in. But we're going to see highly autonomous cars dominating the market. And we're talking about a 77 billion market as well. So it's actually significant. So where is this going to be? Well, you probably can't see the colours very well, but you can see that actually the markets for the US and Europe are about the same in size. Now that's quite interesting. But the key market is the green one, which you can't see very well, but that is the sort of the Southeast Asia, Asia-Pacific region market. That is massive. And so if you are going to target this market, you really need to be moving into that market, because that's where the big opportunity is. And this is why we need worldwide standards around this. So the biggest opportunities are in here, and actually, as I said, the software sector is the one which is likely to benefit most. And of course, companies like Google and IBM are positioning themselves to be in this. And there's lots of companies thinking about how they do that as the cars move to more and more towards a smartphone on wheels, in a sense. Now, the other thing which is happening is that car ownership is predicted to decrease in the future. So we're getting a lot more cars on the road, but we won't be owning them in the future. We will be just using them as a mobility solution. So Uber, we're going to hear from Uber in a minute, but basically you can see that they've grown very, very rapidly. And there's a big interest in self-driving cars because, of course, if you don't need the driver in the car, then that's a cost for the company, and so that's a major benefit. And you can see that other companies are positioning themselves as well. So GM bought Lyft, or $500 million stake in Lyft, which is a rival to Uber. And also they bought Cruise Automation for $1 billion. So they're trying to put these technologies together to try and come up with these mobility solutions for the future. And actually, it's really a natural fit for self-driving cars. If you have a car that drives itself, there's lots of potential applications for mobility solution providers. So, and also, increasingly, private ownership is not a high priority for people. So it removes the hassle of driving when it might not be possible. So if you want to go social drinking, for instance, and maybe you don't take a car already, but also you don't have the responsibility for maintaining the car or for insuring the car as well, which are all hassles for people. And so people quite like the idea of this, particularly the younger generation, which more and more are living in urban environments. So they tend to use public transportation more anyway. Interestingly, Elon Musk has also highlighted that he has plans for car sharing around the Tesla, so Tesla owners can actually lend out their cars to other people to share their cars with other people. So this concept is becoming more and more prevalent. Now, this does introduce some interesting societal changes. So there are some key changes. First of all, we've got the introduction of the internet connectivity to cars. So we've got far more opportunities for infotainment. So our car could become our office in the future, particularly if it's a self-driving car. We could just sit in it and do whatever we want in the car, do work, surf the internet, etc., listen to music, or actually do something creative. But the move to autonomous vehicles will improve safety and traffic flow and reduce emissions, which is all very good. And we've also got these mobility services. There's many positive impacts of that, but there are threats from this as well. There's a threat of automation to jobs. So, of course, if we don't need drivers, there's a whole raft of jobs which are going to change, and people need to think about how that impacts society. There's also other interesting, quirky things which will happen. So if you get more than about 7% of the cars on the road as autonomous, it actually regulates the whole traffic flow. And effectively, traffic becomes a train. Now, what does that mean? It means that if you get up late in the morning to go to work, and you wanted to get into the traffic and try and get to work by driving a bit quicker than you normally would do, you've no longer got that option. So it means the whole of society will need to be regulated to do that. Now, the good news is probably be working from home anyway, so that's the good news. So there's some interesting quirks from that. So concluding remarks, then, first thing is that there's major research opportunities, and the major research opportunities is really addressing a global market, and you really need to think at the global level in this. It's not just the EU and the US. You need to think about the whole world. There's opportunities both in the vehicles themselves, but also in the infrastructure. And we can see a number of things. Increased automation, there's lots of cyber-physical systems areas. We need to think about trust. We need to think about safety. We need to think about liability. How do we deal with those? Also about AI, some of the ethical issues of AI, which are to a certain degree overplayed in some of the scenarios I've seen. But there are other issues which we need to try and do, particularly in transparency. We need to understand basically how the AI is actually making its decisions within some of these systems. Traffic management, big data analytics is very important here, AI for optimization of these systems. Health monitoring, big data analytics again for monitoring systems. Infotainment, 5G has a role to play here, I think, in providing lots of content to people that they might want. But also 5G has very low latency, so you might think about 5G for car-to-car communications to a certain degree to actually do braking of cars or to transfer information between cars. There's also new opportunities for services. And actually, this is probably the biggest growth area for the future, so I'm very pleased that Uber will be on after me, leading to new players in the market. And an issue will be the societal changes that all of this may bring in the future. Okay.
Thank you very much, Hayden. Malcolm, I believe that was the perfect segue to your presentation.
Well, thank you, David. Thank you, Hayden, as well. And I suppose good afternoon now to everyone here. My name is Malcolm Glenn. I manage a lot of our relationships with issue groups and advocacy organizations and nonprofits at Uber right here in DC. So I took a less than 10-minute Uber to get here. I think it's probably the shortest commute of anyone here. And I have been at Uber for a little bit more than 2.5 years. And unfortunately, I don't have any slides, so I'm just going to sit here and hopefully you won't be too tired from hearing me talk. But I've been at Uber for just over 2.5 years. And before I came to Uber, I spent almost 3 years at Google. And at Google, I was very focused on, I worked very closely with the CFO, and I was very focused on sort of the financial impact of a lot of the work that we were doing. At Uber, I'm very focused on the very practical impact that our technology and platform has, and particularly what that impact looks like from the perspective of traditionally underserved communities. And so that's both the platform as it exists today, as well as potential outcomes for future technologies like self-driving vehicles. So it's certainly no secret, and Hayden talked a little bit about our engagement in this space, but we're very, very actively involved and have made some fairly significant investments in autonomous vehicles over the last number of years, for a whole host of reasons. Obviously, there is an economic reason from the perspective of the drivers, but I'll talk a little bit later about why I actually think autonomy will increase the number of drivers, particularly in the short and medium term. But there's some real existential questions that we hope to answer by implementing autonomous technology that will be quite profound from a global perspective. So thinking about a safety conversation, there are 1.3 million people who die in car crashes every single year. About 94% of those crashes are the result of human error. So you're talking about more than 1 million people who die every year around the world in car crashes that could be prevented because they're the result of some mistake that a person has made. If you try to quantify that in economic terms, autonomous vehicle technology could result in something like $1.4 trillion in savings when you take into account avoided crashes, when you take into account things like congestion delays that are then removed, and the efficiency that people have and the time they get back. And then you think about a utilization question, an efficiency question. So for most people, in the United States at least, and in many parts of the world as well, the second most expensive asset that they will purchase in their entire life is their car after their house. And a car sits idle, on average, for 95% of the time that you own it. So it is a terrible utilization. It results in cities investing more and more in parking spaces and parking garages and efforts that I think devalue the way that we could be thinking about future infrastructures for cities. And I think the opportunity to open up cities to be used in a more efficient, more effective way is a really exciting proposition for us and something that we're excited to get involved in as we build out this technology. So I think there's a lot of real potential, but the reality is it's a very young field. We have been at this for about 3 years. We are about an 8 or 9 year old company. And I think there are a lot of barriers in place that are going to prevent us from getting where we are today to the sort of fully autonomous future that a lot of folks talk about. And Hayden mentioned some of these things. I think the first thing is the regulatory environment. There is a hodgepodge and a sort of patchwork nature of engaging with autonomous technology thus far, both in the United States and in other parts of the world. There are some bills making their way through the federal government, and there are numerous different ways that states are approaching autonomous vehicle technology legislation, notwithstanding all of the different regulatory environments that are taking place outside the United States. And so we have a long way to go before we get a regulatory framework in place that will allow for some sort of proliferation of autonomous vehicles. The second thing is the technology. And obviously this is a space where lots of companies are investing very heavily, Uber included, and getting the technology right where we can get to that level 4 autonomy that Hayden talked about is still a ways away. And then, of course, there's consumer acceptance. And we looked at the BCG study that talked about leading executives from car companies. But when you look at some of the studies that have asked the general public what they think about this technology, there's still some aversion to it. And I think we have a lot of education to do to get people comfortable with it. And I actually think when you think about the delivery mechanisms for autonomous vehicle technology, this is why a fleet model, a model on top of an existing network like Uber, I think makes a lot of sense in getting people comfortable with autonomous technology without them having to make the investment that one would need if they were buying the car themselves. Excuse me. Bless you. And so we established something we call an Advanced Technologies Group about 3 years ago in Pittsburgh, Pennsylvania. And this is the engineering center where we develop our autonomous vehicle technology, where we put the kit on top of existing cars and put the cars out on the road to do testing. And ATG was really established to do, at its core, 4 different things. And one is ultimately to replace personal vehicle ownership. And that is an exceptionally lofty goal, but a goal that we take very seriously and a goal that we're starting to already cut into. About 10 to 15% of Uber riders in surveys that we've conducted have said that the availability of Uber has actually changed their calculus around owning a car. And that's just in the context of the existing network as it stands today. Obviously, we want to reduce fatalities and injuries in car crashes. We want to reduce carbon emissions and make cities greener. And then we ultimately want to provide affordable and accessible transportation And you heard a little bit about some of the potential value for people with disabilities, people who are seniors, people with mobility issues. Autonomous vehicle technology has the opportunity to significantly transform mobility for people who have traditionally had a really hard time getting access to transportation. So we have, since the fall of 2016, been testing on the road in a couple of different cities. Pittsburgh, Pennsylvania, and Tempe, Arizona are the ones where we've done the most prominent points of testing. But we suffered a real setback a couple of months ago in Tempe, Arizona. I'm sure folks in this room have probably heard about the accident that took place in Tempe in March of 2018 when one of our cars struck and killed a woman who was crossing on a dark road in Tempe, Arizona. It was a horrible tragedy, certainly for her family. And it was also a real setback for our team because ultimately we have a bunch of folks coming to work every day looking to solve big problems. And I don't think they had the expectation, particularly this early in the context of our work, that they were ultimately going to have to deal with a fatality. But as Hayden mentioned, I think this is something that the rest of the industry is also grappling with. The reality is we're not going to go from 1.3 million people dying to 0 people dying, and certainly not going to do that overnight. And so grappling with the reality that there are going to be fatalities, and we do have to figure out why those things take place and get to the bottom of why the technology potentially didn't work the way we thought it was going to be, is a really important, I think, reckoning moment for the industry. What we did in the aftermath of that is we grounded all of our testing vehicles indefinitely. They stay grounded today. And we are working with NHTSA and the NTSB in their ongoing investigations to understand exactly what happened. We want to make sure that before we get back on the road, this technology is as safe as possible, and we can make sure that we learn what happened in this instance and make sure we mitigate something like this happening going forward. But prior to that, we were making a lot of really significant progress that I think was helping inform the way we think about this. So we had accomplished more than 2 million miles driven in our autonomous vehicles, and we had actually given more than 50,000 Uber X rides in autonomous vehicles. And this means real people requesting an Uber, not knowing that they were going to get matched with an autonomous vehicle, having that autonomous vehicle come up and pick them up. They have the option to say no if they'd rather not take an autonomous vehicle. But the vast majority of people actually said, let's try this. There's a person behind the wheel. There's a person in the front seat collecting data. And so we had 50,000 people take these rides, give us their very important qualitative feedback, and help inform how people think about this technology going forward. And again, this wasn't on test tracks. This wasn't under conditions we could control. This was on real roads with real people. And I think that was really, really important in helping us kind of continue along on this vision that we have. You know, the question, why Uber? You know, there are folks that have been at this for a lot longer than we have. When I was at Google 5 years ago, one of the only players that was really serious about this work was Google's self-driving car project. And now you think about all of the car manufacturers, all of the tech companies, the sort of hybrid companies that do transportation and technology like ours. Lots and lots of folks recognize the potential in a way that they didn't before. So why do we think we are well equipped in some ways to do well in this space? Well, I think the network really matters. And when you think about the network that we have, 67 different countries, about 450 different cities, we get 15 million rides every single day. We accumulate almost 2 billion miles driven around the world every single month. And that helps inform where people want to go, where it makes sense to deploy and test. And understanding the ways that people think about transportation, that's really, really important. And we have a really significant motivation behind this because we are one of the few companies that has been deeply, deeply ingrained at this context, this confluence of ground transportation and technology. And that's really kind of the core of our business. And so we don't think about this as a sort of side project or as something to do kind of away from the core business. This is a very natural progression of the business that we've built over the last 8 or 9 years. And so I think this is something that is going to continue to be deeply, deeply important to us. So as I mentioned, we were on the road in 2 different cities, and I think we have plans over the long term to launch in more and more cities to do more testing. And so the question we often get is, what does it take to launch in a city? And so the first thing we have to do is we have to map the city in extreme high definition. And this is very different than the way that a Google Maps or an Apple Maps or a Waze maps the city for turn-by-turn instructions, but we're mapping the city in high definition down to the centimeter so that our cars can see everything that exists within a city infrastructure, and be able to understand what those things are. And as those things change, making sure that they adjust to make sure that they're changing along with it. So we choose set routes. We then layer our self-driving cars into our existing UberX fleet. And when someone requests a ride that goes along a route that we have mapped and we have programmed for, they may get matched with a self-driving UberX. We're consistently and constantly making adjustments, making sure that the cars are adjusting to different experiences that they're seeing on the road. And over the course of the time that we've done this, as I mentioned, we've accumulated a lot of data, a lot of miles driven. And people sort of will often ask us what's the value of doing this in the real world versus on test tracks? Obviously, there's a greater safety concern, which we've experienced very concretely by doing this on the road, but we think that there's some real valuable data and qualitative information that one can glean from doing this in the real world. And so we're always learning, and that learning never stops. And so we need to answer some very fundamental questions from our riders. Things like, what does this feel like? Do they like it? Do they trust it? There's an opportunity in the back of a self-driving UberX ride where you can press a button on the iPad that shows what the LiDAR is seeing at any given moment to stop the car. Thankfully, we've never had anyone in the 50,000 UberX self-driving trips that we've conducted decide not to continue their trip. And so we're getting to a level of trust that we didn't have before we conducted this testing. We obviously have a long way to go. 50,000 is a good number, but it's a small drop in a large bucket when it comes to the transportation ecosystem, but we are making progress. And again, this is why I think the fleet model makes the most sense. When you think about some of the things that Hayden mentioned around cost, the Google car is somewhere in the range of $150,000 when you think about all the technology that's put on top of that car. This is going to be prohibitively expensive for many portions of the population, particularly when you think about folks from traditionally underserved communities, folks who traditionally have substandard access to transportation and transportation infrastructure. Ferrying this technology into an existing fleet model is a way for people who do not have access to robust resources to take advantage of it. And it's also a way for people to understand whether it's something they feel comfortable with before making that huge investment, even if they can afford that investment. And again, the network of our fleet and the degree to which we're already starting to at least change people's calculus around individual car ownership is, I think, something that will only increase when you think about the engagement of self-driving technology. But I think the real future and the real value that one can unlock in the context of the impact on cities, the impact on safety, the impact on efficiency and utilization is when you think about autonomous cars that are also shared and electric. And there's still some real challenges that we have before we can get to that point. So we think about each of these things individually as they exist on our platform today. Of course, our shared trip option is Uber Pool. Uber Pool is about 20% of the trips in the cities where it's operating, and it's about 30 or 40 cities around the world. 20% is great, but we have a long way to go to start to reap the real benefits that one can achieve by having people share rides to get more butts in seats, as we like to say internally. We have a long way to go from electrifying parts of our fleet. We're going to announce a really exciting initiative today whereby we're going to work with about 8 or 9 North American cities to get about 5 million trips through electric vehicles in the next year. And we have some really lofty goals in places like London to transition the cars that our drivers use from diesel to electric vehicles. But there's some real technological challenges as the technology exists today. As Hayden mentioned, they're very, very power-hungry tech, and being able to get that to work with electric vehicles is something we're not quite ready to do yet. And then obviously autonomous vehicle technology unlocks a whole host of things from an efficiency and a safety standpoint. So we think about this as a future that is shared, that is electric, that is autonomous. We have a long way to go to get there. And I think the other interesting thing to think about is it doesn't necessarily need to only take into account cars. And so we're increasingly thinking about Uber as a mobility platform. You'll have seen that we recently purchased a company called Jump Bikes, which is a pedal-assisted company based here in the United States that allows people to, for a very short trip, pay a very low cost to get a bike that locks to any structure in a city and it can get them around. You'll probably have seen the proliferation of scooters in a number of American cities. That's a space that I think is very interesting for us. But then we're also thinking about driving folks to other entities like public transit. So we recently announced a partnership with an organization called Masabi, and Masabi handles ticketing for transit organizations in about 30 different cities all around the world. And so the goal, I think, for us in the future is you can open the Uber app, take a scooter if it makes sense, take a bike if it makes sense, take a self-driving car if it makes sense. We're actually starting to explore engagement in the VTOL aircraft space, not the unmanned VTOL aircraft space, but you can imagine a future where you can actually get an aircraft to take you where you want to go. Autonomy is going to be a part of that, but for the short and medium term, autonomy is still not going to solve for many of the use cases that people have. And just to close, just to give you some perspective of the scale in which we're operating, we're still only less than 0.5% of miles driven on the road. And when you think about where our ambitions are, so, I think it's fairly reasonable that we can get to something like 10 or 15x the size of where we are today in the next 10 or 15 years. And so even if we do that, you're talking about, right now we have something like 600,000 drivers on the road in the United States and about 2.5 million drivers on the road around the world. Even if you think about a future where half to 70% of our fleet in 10 or 15 years is autonomous, you're still talking about a portion based on our scale that is going to be more drivers on the road today, more drivers on the road in 10 or 15 years than there are on the road today. Dealing with edge cases like how do we strap in and transport people who use power wheelchairs, and we're building out a fleet of power wheelchairs on our platform today that I think is going to help inform the way we think about it in the future. And so I think it's very important to have the conversations around what automation means from the perspective of disruption and changing the way that workers engage with driving. But I think there are actually a number of really unique opportunities that stand to be created by autonomous vehicle technology, and we're excited to figure out how we can help the drivers who are driving on the platform today transition into a future where they can continue to drive, and also to think about how we can develop workforce development programs to help drivers who are no longer going to be driving in the future find ways to engage with that new economy in whatever way makes sense for them. So I will stop there. I know we may be a little bit pressed for time, so I'd love to make sure we hear from everyone with their questions.
Excellent. Thank you, Malcolm. So I'm sure we have questions. Yes.
Question for Malcolm.
Hang on just a moment.
Since it's fresh in my mind. Clearly and no doubt, Uber is revolutionizing mobility, amazing things that you're talking about. How are you going to bridge, and you're probably thinking about this as well, underserved communities that are not in urban environments that drive the fact that they're under or unemployed because they simply don't have access to a car or even public transportation?
It's a really
you've created and filled supply and demand in very dense locations. How are you going to spread this model?
It's a really good question, and it goes back to this thought that I regularly have, which is there was a study a number of years ago that showed that the greatest determining factor as to whether someone can climb out of poverty is actually commute time. And so this is very existential when it comes to economic mobility, and something we're very thoughtful about. Literal economic and other forms of mobility. And so we think about this all the time in terms of getting supply and demand right. We're making some fairly significant inroads. When you think about penetration in the United States, and we don't have exact numbers on what proportion of the population we cover, but we're in remarkably suburban and increasingly rural areas, certainly when you think about where we are today versus where we were, say, 2, even 3 years ago. But we haven't covered everywhere, and the further out you are, the more difficult it is to get an Uber. So one of the things that we're thinking about is how can we utilize other parts of the platform to start to engage in rural communities in ways that we haven't before. So one of the things that we launched a number of months ago is a product called Uber Health. And this is a way for hospitals, clinics, other medical institutions to actually procure rides, deploy them to people who need to get to non-emergency medical appointments, and help those people do so even if they don't have a smartphone. So you can actually sort of sit at a database, get the rides to the right people, get the people to where they need to go. This is increasingly an issue in rural areas. And so non-emergency medical missed appointments is a huge, huge strain on hospitals. And it's disproportionately a problem the further and further you get from city centers. And so what we started to do is get hospitals and folks in rural areas more comfortable using Uber through the context of something like Uber Health. That doesn't necessarily solve for the people who are trying to get around who aren't missing their medical appointments who live in rural areas, but we recognize that we can control for supply and demand to some degree, and we've done a pretty good job of that, but to the degree that we have to go outside the traditional model, let's use things like Uber Health. Let's also think about some of the things that, one of the slides from before said that Elon Musk thinks about people using their own personal vehicles to give rides in an autonomous future, even when they're not using it. So you can still buy a car, but you can also still increase utilization and have people sharing your car. That stands to be something that people in rural areas would benefit from disproportionately relative to people in urban areas. And so we want to eliminate car ownership. The likelihood is that we're not going to do that. And so to the degree that there are people who buy autonomous vehicles and want to make money and increase utilization, I think rural areas is a place to start. But in the meantime, let's use other parts of our platform outside the traditional supply and demand model to see if we can get people in rural areas more engaged with using Uber.
Thank you. Ann, and then.
A question for anyone who would like to answer it. So in the context of autonomous technology development, who makes decisions around standards for things like safety, security, trust, transparency, and what are the implications for international cooperation?
So the who is more often than not is industry driven. I find it interesting. You brought up a whole list of things, right? So when we think about standards, standards are normally structured around safety, but generally the way that the industry standards organizations are built, the development of a technology, the application, if they're going to talk to each other, if they're going to interact, because you really can't be safe in an autonomous world unless everything's communicating with everything else. And so setting those standards, whether it be protocols, whether it be the types of data exchange, is generally an industry function. Government is horrifically bad at technology, and so you normally don't want the government setting technology standards that you end up with 30-year-old technology by the time they're done. And you guys pitch in. So
yeah, no, in the aerospace business, certainly you've got the FAA or the CAA in the UK or whoever in Europe who sort of regulates what you can do in terms of flying aircraft and also regulates the sort of weight of the aircraft. So 25 kilograms is a key weight within the autonomous aircraft business. In the automotive industry, there's nothing at the minute. There is no outside body to certify anything, and so it's up to the automotive companies to do that. Now the interesting thing there is that as you move forward, at the moment we insure a car as a person, but actually that doesn't make sense in the future. If you're a passenger in the car and it's autonomous, why would you insure that car? So the insurance liability then has to go to the manufacturer of the car. So it's then the insurance, so the car companies will need to take on that insurance. So there is a need for some sort of certification body for cars, but it doesn't exist at the minute. There's various sort of different bodies that represent the industry, but there's no outside independent body to do that. There's also some interesting things, because I work from aerospace to nuclear, okay, and rail in between. And in aerospace, we always, for a manned aircraft, it's always 10 to the 6, and it's because your chance of having a heart attack for a pilot is 10 to the 6, and so you always have two pilots. You have a pilot and a co-pilot, just in case one of them keels over. If you go to the nuclear industry, in the nuclear industry, you don't want a person in the loop at all. Everything has to be, if you want to drop the rods into the reactor, it's totally automated. You get the human out of that, because the human is seen as the weak point in the system. And so depending on the certification body, some certification bodies will want a human in the loop. And in the rail industry, they always have it where you have an advisory sent to a human who makes a decision to do whatever safety action needs to be done. So there's different levels, and so it depends on whether you need a human in the chain or not. And so some industries will claim 10 to the 9 by not having a human in the loop, whereas other industries will claim 10 to the 6 by having a human in the loop. So there's different viewpoints, and you have to educate the whole of the certification bodies as well, and that's a challenge.
I think I'll just add one point onto what Hayden said. I think it's also the cost model that's associated with that. So, with the unmanned systems, I mean, the whole idea is to try to bring that level, depending on the risk, so maybe 10 to the -5, because otherwise you're driving a lot of the companies out of business if you wanted the same certification level as you do with manned aircraft.
Yeah.
I'd like to find out more about the incident in the Tempe where the pedestrian was killed by the autonomous vehicle. Was the circumstance, did she dart out in front of the moving vehicle so the vehicle did not have time to stop, or would it have been any different had it been a driven vehicle? Or, if you dart out in front of a moving vehicle, regardless of whether it's a bus, a train, a plane, a driven vehicle, or autonomous, would that issue be the same? If compared to, say, I just saw the other day, a drunk driver in Michigan sentenced for killing 5 bicyclists while drunk. Why is you see what I'm getting at? Why is the issue so great that there's so much great tragic when an autonomous vehicle hits a pedestrian than when a driven vehicle hits the pedestrian? I'm not sure what the circumstances.
Yeah.
But also in the rural areas with autonomous vehicles, from personal experience, I know straight away driving in rural areas at nighttime that you can deal with, like deer crossing the road, more than one. So, would it be any different with that pedestrian in Tempe than with a deer crossing the road? So I guess I don't know what the issue was in Tempe, but why is it so much greater a tragedy when an autonomous vehicle hits a pedestrian than when a driven vehicle hits it? Would that, you see what I'm trying to get at?
Yeah. I'm happy to answer just about the specifics of the Uber question. We want to find out what happened too, and so we grounded our vehicles, which was good from the perspective of helping people feel safe in the aftermath of a tragedy, but also means that we don't necessarily know exactly what happened. So we're cooperating with the 2 investigations, and once they issue their full reports, I think that'll help shed some light on it. I think the broader question, why do people perceive a pedestrian death with an autonomous vehicle as different than the 6,000 pedestrian deaths that take place just in the United States every single year, none of which get any really news coverage, is because part of our stated and very sort of existential reason for making these investments is because of the safety calculation, is we want to save lives. And so I think people are thoughtful about the autonomous technology not doing that and what that potentially means. I think the other reason is because there is some fundamental distrust and lack of awareness around autonomous vehicle technology. And so if people have misperceptions or fears about this technology, and they see a story about a person dying as a result of a self-driving technology, that confirms a lot of fears that they already have. And I think that results in them reacting in a more outsized way than what the nature of the tragedy is. In terms of the technology, should the technology be able to see a deer at night? Should it be able to see a person darting out at night? That's the goal. that's exactly what we're trying to mitigate against. So even if it's dark, it doesn't matter. A person wouldn't be able to see a person in the dark, but the goal is to get the technology to a place where the technology can see those people, and so we can avoid situations like this going forward.
It's interesting because there have been some studies of people's reactions to the technology, and what they found is that really it needs to be 1,000 times safer before they will accept the technology, and that's a fundamental issue. But I think you get down to the ethical question of how many people are dying a day.
6,000 in
6,000.
pedestrian.
So we could introduce a technology tomorrow which would reduce that by a significant proportion. And also all of the costs of insurance costs for hospital for the people who are badly injured, which is also a big issue. I mean, ethically, should we just go with the technology or not? And that's the big question for society. I mean, people talk about the ethics of a few people being killed by the technology, but actually, ethically, can we not introduce this technology because we would save thousands of lives immediately?
And that's the point that we constantly get to. I can tell you that the last 15 years I've been hitting this on the unmanned aircraft system standpoint, is that I can demonstrate conclusively that using unmanned aircraft systems in a variety of applications guarantees that fewer people will die. Guarantees it. But the level of trust that people want to put into an automated system, we do expect perfection, right?
Yeah.
And so for example, the few deaths from the Tesla autopilot, right? The people who were driving those cars tended to be early adopters, high-tech kind of people. That's the reason they have a Tesla. And the system works remarkably well. 99.99, it's going to work really well. It's going to hold your lane. It's going to slow down when it's coming up on another car. It works really well. It's a driver assist. It's never marketed as anything else, which means you're supposed to sort of keep situational awareness. And you're supposed to keep your hands near or on the wheel just in case, right? But we begin to trust it. We get comfortable with it because it works so well. And so next thing you know, people are reading books, their heads down, they're writing novels on their phone, and by the time they look up, and they begin to ignore alarms, right? So in most of the Tesla accidents, the alarm went off. And in some cases, up to 6 seconds before impact, and the person behind the wheel, in one case, did not put their hands on the wheel after 6 seconds of alarm. And so that tells me that that person is probably very comfortable with the system and had alarmed for them a few times before, but it took care of it. And so once again, your mind starts to wander. So there's not enough trust of automation, and there can be too much trust of automation. Until we get it to an infinitesimal number of nines, there are going to be situations where wrecks are going to happen. But I will submit that we're already at the point where far fewer wrecks would happen if everyone had this technology at their disposal. So the acceptable loss is one of perception. We accept that humans are not perfect and that they're going to make bad decisions. We can accept that and we live with it because we are. We expect so much more out of our technology.
Yeah, I mean, I used to design control systems for jet engines, and basically there we would design the control system to survive a fire for 2 minutes. And the reasoning behind that is that the pilot won't see the alarm straight away. So the pilot will be doing something and then they might catch the alarm that they see. And so you need to be able to design in that factor that the human is there and won't always do what you expect when you expect them to.
All right, I've been given the sign that we have one last question.
Okay, so going back to the fact that this is transatlantic collaboration, I had a question linked to an area of collaboration. So you mentioned that there was a lot of work to map the routes to the centimeter. This is mobility across a city. So it's work that can be shared by different, not only Uber, I mean, there are public authorities, etc. So my question is this a concrete area of collaboration that could be taken up in Europe, in the US, across, the world, because as you said before, there's the world, that could be started concretely to speed up the uptake of mobility?
Yeah, that's a great question. And I think the answer is yes. And I think in part the answer is yes because we don't necessarily need every car, even on the Uber network, and there are going to be other networks, we don't need every car to be an Uber technology car. So part of the reason I think it's really good that there are so many other players doing this testing in other cities is because we see a future where some of the cars that you request may be cars that are fed to you by Uber. Some of them may be fed to you by other technology companies that have invested in this themselves, that have mapped cities themselves, that are looking for basically a means of deployment, and Uber is that means of deployment. So when you request a ride, you don't actually know from sort of what entity that car comes. It's exactly the same experience for the end user. But on the back end, it could have been a company from a different country. It could have been a company that is investing in a slightly different way, that's only working on the LiDAR, that's only working on the HD maps. And so I think we're still relatively early in the space to see what robust deployment looks like. But at a core level, yes, the more people that are investing in this space and building out the technology, and the quicker we can get the technology to a place where it does work in such a way that people are comfortable with it, and you have these networks like ours that can help deploy that technology in a really robust and quick way, I think that's just going to mean it gets into the hands of people more quickly. So more people investing in this, I think, is better for everyone.
Let me say again, thank you to our panel. I think we've had a fascinating conversation, series of presentations, and help me give them a thank you.